Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. A pale river of light flows across the night sky. On a clear, moonless night far from city lights, you can see it arching overhead, a ghostly band shimmering against the dark. For millennia, humans have gazed at this milky glow with wonder. They gave it names born of poetry and legend: a river of heaven dividing the sky, the spilled milk of a goddess, a trail of campfire smoke from cosmic hunters, the path of migrating birds. Under these countless stars, our ancestors wove tales to explain the mysterious band, never realizing they were part of it. That hazy luminosity is no mere cloud or myth. It is the combined light of billions of distant suns, too many and too faint for the naked eye to resolve individually, blending into a continuous glow. You are looking edge-on into our galaxy, seen from within. I am that galaxy, the Milky Way, your island home in the cosmos. In my embrace, I hold everything you see in the night sky, and so much more beyond. My light takes tens of thousands of years to reach your eyes, traveling across the vast gulfs of space, from stars scattered through my spiral arms. When you behold the Milky Way on a dark night, you are peering into the heart of our galactic home, an immense congregation of stars, gas, and dust, shaped like a great wheel in space. From your vantage point on a planet nestled within me, you cannot see my entire form, only this faint band of starlight that rings the sky. Yet across centuries of curiosity and science, you have begun to unveil my hidden shape. I speak to you now as a storyteller from within, the voice of the Milky Way itself, to guide you on a journey through our galaxy. Hear my tale of how we discovered our place in this stellar city, of the wonders and mysteries that lie in my depths, and of the cosmic dance that connects all who dwell here. Let us begin where all stories start, beneath the same endless stars, with you looking up in awe at the Milky Way, seeking to know what it truly is. You see, living inside the Milky Way makes it hard to grasp its full shape. For a long time, humans could only guess what form our galaxy took. We are like ants trying to discern the shape of a giant tree while crawling along its bark, or travelers lost in a forest unable to see the outline of the woods. Gazing at the Milky Way from within, we see a band of light, but not the grand design. Early astronomers counted stars in different directions and noticed more in the band of the Milky Way than above or below it. From this, they deduced that our stars form a disk, a flattened, circular swarm rather than a sphere. Still, early maps were deceiving. Without knowing about obscuring dust, some 18th century star counters assumed the sun was near the center of this grindstone of stars. It was only in the early 20th century that the true enormity of our galaxy became clear. By charting the distances of globular clusters, those ancient, tightly packed star clusters orbiting the Milky Way, astronomers realized that the clusters were centered around a point in the constellation Sagittarius. This meant the real heart of the galaxy lies far from our solar system, tens of thousands of light years away towards Sagittarius, hidden behind dense clouds of stars and dust. We had been off to the side all along, in the galactic suburbs, not the downtown. With better observations, the picture sharpened. The Milky Way is a vast spiral galaxy, shaped like a disk with graceful spiral arms unwinding from a bright central bulge. In fact, at the very core, I possess a bar of stars, a straight band crossing the middle, with spiral arms attached to its ends like ribbons. Imagine a giant spinning pinwheel or a whirlpool in space. That is my form. My disk spans about 100,000 light-years across, yet it is relatively thin, only a few thousand light-years thick for most of its width, thinning out toward the edges. In the center, a bulge of older stars rises above and below the disk, a spheroidal hub glowing golden with ancient light. And enveloping everything is a faint halo of old stars, and much more, as we will see. How could you discern all this while stuck inside? It took ingenuity and new ways of seeing. You traced the spiral arms by mapping the clouds of gas that emit radio waves, which can penetrate the dust. You measured the distances and motions of stars all across the sky, slowly piecing together a map of the Milky Way. It was like mapping a city at night from within, seeing only nearby streetlights, but inferring the city's layout. Bit by bit, the spiral structure emerged, multiple arms coiling around the center, our sun residing on a minor spur between two larger arms. Even though no one can yet take a photograph of the Milky Way from outside, you have built a mental picture from countless observations, a cosmic portrait of our home galaxy. Thus, hidden from ordinary sight, my shape has been revealed in your imagination. A flat spiral disk with a central bulge and bar, surrounded by a tenuous halo. Whenever you look at that milky band in the sky, remember that you are peering along the plane of this disk, through spiral arms of stars and dust. From the inside, I may appear as a hazy band, but in truth, I am a grand spiral, turning slowly in the darkness of space. To truly know me, you had to step beyond human eyesight and trust the messages carried by all forms of light and gravity. In doing so, you discovered the magnificent structure that I am, the Milky Way, unveiled from within. Our sun occupies an unassuming corner of this galactic metropolis. We reside in a minor spiral arm known as the Orion Arm, a lesser spur of stars and nebulae, not one of the Milky Way's primary spiral arms, but a side branch. The Orion Arm threads its way between two larger arms. Closer to the galactic center is the Sagittarius Arm. Farther out is the Perseus Arm. Think of it as a small tributary between giant rivers of stars. Here, about 26,000 light-years from the galactic center, the Sun and its family of planets orbit in relative calm. We are far from the bustling, crowded core, in a quieter celestial neighborhood with ample elbow room between stars. The Sun is an ordinary star among hundreds of billions, shining with a yellow warmth as it drifts along the Orion Arm. In our vicinity, stars are well spaced. The nearest star system, Alpha Centauri, is roughly 4 light-years away. That's 4 years at light speed, or about 25 trillion miles of empty space between us. Such distances mean that to the Sun, its stellar neighbors are like distant lanterns. Our local region is actually a sparse bubble. The solar system is currently passing through a cavity in the interstellar gas, a local bubble carved by ancient supernova explosions. Within this bubble, the gas density is low and hot, a testament to long-ago stellar deaths that swept out a pocket in the Orion Arm. Even so, beyond this bubble lie clouds of gas and dust that trace the Orion Arm, including famous nearby star-forming regions like the Orion Nebula, only about 1,300 light-years away. In the grand rotation of the galaxy, the Sun moves at about 230 kilometers per second around the center, fast by human standards, yet it takes roughly 230 million years to complete a single orbit. This period, sometimes called a galactic year, is immense. Since the Sun's formation 4.6 billion years ago, it has circled the Milky Way only around 20 times. To put it in perspective, during the Sun's last orbit, dinosaurs were just emerging on Earth. It will take another full rotation to carry us to a time far beyond the present day. We are tiny passengers on a very slow merry-go-round. Our location in the Orion Arm may well be fortunate. It lies in the galactic habitable zone, a band of distances from the center that might be conducive to life. Here, we are distant enough from the volatile central regions, with their frequent supernovae and intense radiation, yet close enough to have a richer mix of elements heavier than hydrogen and helium, the kind needed to form rocky planets and biology. In these suburbs of the galaxy, life had the opportunity to arise on at least one world. From this vantage point, midway out on a minor arm, the night sky offers a spectacular view of the Milky Way's internal structure. We see the dense star clouds toward the galactic center as a bright glow in Sagittarius, and we see dark rifts, where interstellar dust in the arm obscures distant stars. The Orion Arm is our cosmic neighborhood, and while it may not be a major spiral arm, it is home. In its relative quiet, our Sun and Earth have circled in peace for eons, a small part of the Milky Way's vast tapestry. Unremarkable though our position may be, it gives us a front-row seat to view and study our galaxy from within. Riding the Orion Arm, we have learned that we are part of a rotating disk of stars, and that our Sun is one modest star among billions. From this perspective, we can journey outward in our imagination, from our local stars to the broader galaxy, knowing where we stand in the grand scheme. We are inhabitants of the Orion Arm, on the outskirts of a great spiral, looking inward and outward at the same time. Within the Milky Way's sprawling collection of stars is an astonishing variety of stellar life. Not all suns are like our Sun, far from it. There are stars so massive and bright that they blaze blue-white and burn out in a few million years, and stars so small and cool that they barely glow red, destined to shine for trillions of years. The most common stars in our galaxy are red dwarfs, feeble embers with perhaps a tenth the mass of the Sun. They are faint. None is visible to the naked eye from Earth. Yet they are legion, forming the backbone of the galaxy's star population. On the other end of the spectrum are giants and supergiants, behemoths like Betelgeuse or Antares, hundreds of times larger in diameter than the Sun and tens of thousands of times more luminous. These titans live fast and die young, exploding as supernovae that briefly outshine entire galaxies. Between these extremes lies every color and type of star. Yellow stars like our Sun, white stars hotter than the Sun, orange dwarfs slightly cooler, and many more. Some stars live in clusters. Born together from the same gas cloud, they form sparkling groups like the Pleiades, and gradually drift apart over time. Others are loners. Many, perhaps most, are in binary systems, two stars orbiting each other in a gravitational dance. Some binaries are so close that they exchange gas or even merge. Others are widely separated, circling leisurely. The night sky's familiar stars are a mix of these types. The bright bluish Sirius, actually a binary with a faint white dwarf companion. The golden Arcturus, an aging giant. The red twinkle of Antares, a supergiant nearing the end of its life. Each has its own story. Stars are not eternal. They are born in nebulae, live out their spans, and eventually perish. Smaller stars like the Sun swell into red giants and gently shed their outer layers, leaving behind their hot cores as white dwarfs, Earth-sized embers of incredible density. A single spoonful of white dwarf material would outweigh a car. These white dwarfs slowly cool over billions of years, fading into darkness. More massive stars die more violently. When a star much bigger than the Sun exhausts its fuel, its core collapses in a catastrophic implosion, triggering a supernova explosion. In that instant, the star's core is crushed into an ultra-dense nugget called a neutron star, or, if the star was massive enough, a black hole. Neutron stars are cosmic oddities. They pack more mass than the Sun into a sphere only a few kilometers across. The matter inside them is so compressed that atoms themselves break down. They are essentially giant atomic nuclei made mostly of neutrons. If you could scoop a teaspoon of neutron star material, it would weigh billions of tons. Spinning neutron stars become pulsars, emitting beams of electromagnetic radiation from their magnetic poles. As they rotate, sometimes hundreds of times per second, their beams sweep across space. If one of those beams crosses Earth, we see a pulsating signal, a cosmic lighthouse blinking on and off with astonishing regularity. The first pulsar was so regular, it was jokingly nicknamed LGM for little green men, since no natural explanation was initially known. Now we know pulsars are rapidly spinning neutron stars, the collapsed remnants of supernovae, flashing as they cool. Even more enigmatic are black holes, formed when the core of a very massive star collapses beyond even neutron star density. A black hole's gravity is so intense that not even light can escape from its immediate vicinity. What remains is a true abyss in space-time, an object detectable only by its gravitational effects. In the Milky Way, astronomers estimate there are millions of stellar mass black holes quietly lurking. Most roam unseen in the darkness, but a few betray their presence. If a black hole is in a binary with a normal star, it can siphon gas from its companion, heating that gas to extreme temperatures and causing it to emit X-rays before vanishing past the black hole's event horizon. Such X-ray binaries flicker as the black hole feeds. In other cases, we detect black holes when their gravity bends and magnifies the light of more distant stars behind them, an effect called microlensing, acting like a cosmic magnifying glass. Through observations like these, we know our galaxy is teeming with hidden black holes of a few to dozens of solar masses, each a remnant of a once brilliant star. Beyond these dark remnants, the Milky Way contains other exotic stellar phenomena. There are blue stragglers, oddly young-looking stars found in old clusters, likely formed by stellar mergers. There are magnetars, neutron stars with magnetic fields a trillion times stronger than Earth's, occasionally cracking their crusts and releasing giant gamma-ray flares. Variable stars like Cepheids and RR Lyrae pulsate in size and brightness, serving as cosmic yardsticks to measure distance. In every corner of the galaxy, the diversity of stars is on display, from newborn protostars still wrapped in cocoons of dust, to bloated red giants approaching their final breaths, to the ghosts of stars long dead. And circling many of these stars are planets. Countless planets, making up an astonishing menagerie of their own. In recent decades, we have discovered thousands of exoplanets orbiting other stars in the Milky Way, and we suspect there are hundreds of billions in total. There are gas giants larger than Jupiter hugging scorchingly close to their suns, and icy worlds in the darkness far from their stars. There are rocky planets of all sizes, some in their stars' habitable zones where liquid water could exist. Each star is potentially a solar system, a miniature world system of its own. This means our galaxy is not only a city of stars, but also a vast collection of worlds. Somewhere out there, on one of those myriad planets, there might be other eyes turned skyward, beholding the same galactic panorama. The sheer variety of stars and their planets in the Milky Way speaks to the creativity of nature. From the dimmest red dwarf to the brightest supergiant, from pulsar beacons to silent black holes, every type of star enriches the tapestry of our galaxy. Together, they light up the Milky Way and forge the heavy elements that become new stars, new planets, and perhaps new life, continuing the cosmic cycle without end. At the very hub of the Milky Way lies a crowded and turbulent realm, unlike the relatively peaceful galactic outskirts we inhabit. As we move inward toward the galactic center, the density of stars increases dramatically. In the innermost few hundred light-years, millions of stars pack into a region of space that would fit inside the orbit of the outermost planets of our solar system. If you could stand on a world near the galactic center, your night sky would be ablaze with starlight. Thousands of times more stars would be visible than we see from Earth, and the darkness would be filled with a perpetual glow. This central hub of stars is the bulge of our galaxy, a spherical congregation of mostly old, reddish stars. But amidst this throng of ancient suns, there are also young, massive stars and extreme phenomena. At the core of it all, in the direction of Sagittarius, lurks a gravitational leviathan, a supermassive black hole with the mass of about 4 million suns. This monster sits in the exact center of the Milky Way, anchoring the orbits of stars around it. Astronomers cannot see the black hole directly. It emits no light, but they have traced its presence by the motion of stars that swarm like bees around an invisible queen. Over decades of patient observation, scientists watch these central stars loop around an unseen object at incredible speeds. One star was seen to swoop in and then swing around the dark center at thousands of kilometers per second, completing a full orbit in just 16 years. For comparison, remember that our Sun takes 230 million years to orbit the galaxy. Yet this star whipped around in a mere human lifetime, bound by an enormous gravitational force. Such dizzying orbits provided ironclad evidence of a supermassive black hole in the Milky Way's heart. The black hole itself is quiet compared to the fearsome engines in some galaxies, but it is not entirely inactive. The environment near this dark heart is extreme. Around it whirls a disk of gas and dust, drawn in by its gravity. Occasionally, clumps of this material spiral inward. As gas falls toward the black hole, it heats up and flashes brightly in X-rays and infrared light before vanishing from view. Astronomers have detected these flares, sudden bursts of energy as the black hole devours a bit of matter. It's as if the sleeping dragon at our galaxy's center occasionally stirs, breathing out a brief fire of radiation. Aside from gas, whole stars can be disrupted if they venture too close. Tidal forces near the black hole can stretch and tear a star apart, swallowing the star's material and unleashing a flare. Thankfully, such events are rare. Surrounding the black hole is a cluster of some of the most massive and luminous stars in the galaxy. Paradoxically, these young blue stars, some with dozens of times the Sun's mass, exist in a region where conditions seem hostile to star formation. Their presence is a long-standing puzzle. Perhaps they formed elsewhere and migrated inward, or they might have coalesced from the breakup of a massive star cluster that spiraled in. Regardless, they add to the energetic stew of the galactic center. These massive stars will live short lives and die as supernovae, adding more neutron stars and black holes to the central swarm. Indeed, the galactic center likely contains thousands of stellar mass black holes and neutron stars that have gradually sunk toward the deep gravitational well, congregating around their supermassive cousin. Because the center of the Milky Way is enshrouded in thick clouds of dust, we cannot see it in visible light. To human eyes looking toward Sagittarius, the central region is veiled. But when we peer with radio telescopes, infrared cameras, and X-ray observatories, the veil is lifted. We see a bustling scene, spiral filaments of hot gas, arcs and bubbles blown by stellar winds, and a bright radio glow marking the location of the central black hole. The core of our galaxy is dynamic and alive, a place of high energies and constant change, even if hidden from normal sight. Our Milky Way's center is modest as galactic nuclei go. Many galaxies have black holes, billions of solar masses strong, actively gobbling matter and blazing as quasars visible across the cosmos. By comparison, our central black hole is dormant enough that to an outside observer, the Milky Way might not stand out as an active galaxy. Yet evidence hints that our black hole was more energetic in the past. Huge lobes of gamma-ray and X-ray emission, extending far above and below the galactic plane, suggest that a few million years ago, the black hole may have consumed a large influx of matter, blowing out enormous bubbles of hot plasma. Even now, our galactic heart is not entirely quiet. It's just on a slow simmer rather than a furious boil. In the galactic center, we witness extremes of physics, gravity at its most intense, stellar densities at their highest, and energies that push matter to its limits. It is a privilege of our technological age that we can reconstruct this hidden region in our minds, using detectors that collect forms of light our eyes cannot see. We now know the Milky Way has a dark, massive heart, a black hole that ties together the fate of the surrounding stars, and a lively central hub of activity. This knowledge adds depth to our picture of the galaxy. Not only do spiral arms gracefully wind outward, but deep in the core lies a powerful engine that has quietly influenced the evolution of our cosmic home. The Milky Way is not a monolithic collection of stars born all at once. It is a layered tapestry woven over billions of years. Each component of our galaxy, the halo, the bulge, the thick disk, the thin disk, the spiral arms, contains stars of different ages and compositions, telling the story of how the galaxy grew and changed. By studying the properties of stars, astronomers can read this cosmic history recorded in their light and elemental makeup. One stark difference is between the stars of the halo and those of the disk. The halo, that sparse spherical cloud of stars enveloping the galaxy, is populated by extremely old stars. Many of them formed when the universe itself was young. These halo stars orbit the galactic center in eccentric, inclined paths, often angled oddly compared to the orderly rotation of the disk. They are relics of the Milky Way's infancy, some nearly 13 billion years old, almost as ancient as the universe. They typically contain only tiny traces of elements heavier than helium. In astronomical terms, they are metal poor, because in those early eons, there had not yet been enough generations of stars to forge abundant heavy elements. When we examine the light of an old halo star, we find it composed almost purely of primordial hydrogen and helium, with only a faint seasoning of heavier elements like oxygen, carbon, or iron. This tells us these stars formed before heavier elements became common, before supernova explosions had enriched the galaxy. By contrast, the disk of the galaxy, especially the thin disk where the Sun resides, is dominated by younger stars following nearly circular orbits in the galactic plane. These stars, like our Sun, are comparatively metal-rich. They have significantly higher proportions of heavy elements. The Sun, for instance, contains about 2% elements heavier than helium, seemingly a small amount, but immensely more than the oldest halo stars. That 2% includes all the iron, silicon, carbon, and oxygen that make up our planet and our bodies. It is a gift from earlier generations of stars. The disk's stars range from a few billion years old down to newborn stars still lighting up their birth nebula. With each successive generation, starlight has been slowly coloring the galaxy with a richer palette of elements. Massive stars live short lives and die in supernovae, seeding the surrounding gas with the heavy elements forged in their cores. Later, new stars condense from that enriched gas, inheriting the heavy elements. Layer by layer, the galaxy's material has been transformed from pristine hydrogen and helium into the complex mix we see today, capable of forming planets and life and the very soil of Earth. Within the disk itself, astronomers distinguish a thick disk and a thin disk, two overlapping generations of stars. The thin disk is the flat plane of active star formation and young clusters, extending a few hundred light-years in thickness. The thick disk is a more diffuse, vertically extended component, a couple of thousand light-years thick, composed of older stars with intermediate ages, perhaps 8 to 12 billion years, and intermediate metal content. These thick disk stars likely formed early in the Milky Way's history, or they may even be immigrants, stars from a smaller galaxy that merged with ours long ago. Indeed, evidence suggests that around 10 billion years ago, the young Milky Way collided with a dwarf galaxy, tossing many stars into wild orbits and puffing up the disk. That event could explain why thick disk stars have somewhat lower heavy element abundances and higher tilted orbits compared to thin disk stars. It's as if a cosmic collision in our galaxy's youth stirred the pot, mixing in new ingredients and leaving a thicker, older layer before the galaxy settled into the calmer star-forming mode of the thin disk. The bulge at the galactic center also holds clues to the past. The bulge's stars are generally old and metal-rich, though not as metal-poor as the halo. They likely formed in the galaxy's early years or during subsequent mergers, drawn toward the core by gravity. Some bulge stars show elemental patterns, suggesting they formed quickly in a burst of early star formation. Others might have originated in dwarf galaxies that were cannibalized by the Milky Way, their stars flung into orbits near the center. The bulge is like an archaeological tell, a mound of mixed stellar populations from various epochs, packed tightly in the middle. In the globular clusters that hover in the halo, we find some of the purest examples of ancient stars. Tightly bound groups, all born together over 12 billion years ago. Each cluster is a snapshot of the galaxy's youth. One globular cluster may contain stars so old and chemically pristine that they preserve the conditions of the early universe. Another cluster might have multiple generations of stars, hinting at internal chemical enrichment even at those early times. By dissecting the light of globular cluster stars, astronomers have discovered subtle differences in their chemistry, which together form a timeline of enrichment within the cluster itself. This is a microcosm of the larger galaxy's history. Altogether, the Milky Way's stellar populations form a cosmic stratigraphy, like layers of rock in a canyon, each stratum telling of a different epoch. The halo and globular clusters speak of the galaxy's childhood, when it was first assembling and when the initial stars and clusters emerged from primordial gas. The thick disk speaks of adolescence, turbulent times of mergers and rapid star formation, building up heavy elements. The thin disk and spiral arms narrate the continuing story, calmer times of ongoing starbirth, forging new stars from gas, enriched by all previous generations. And in those new stars and their planets lie the seeds of future stories. Our Sun is part of these later chapters, born about 4.6 billion years ago from gas already rich with the ashes of ancient stars. In its makeup is the legacy of countless supernovae and billions of years of cosmic alchemy. Thus, every star carries a memory of when and where it formed. By decoding those memories, a star's motion and the elemental fingerprints in its spectrum, we can trace the lineage of different groups of stars. We see that the Milky Way grew like a living organism, adding material, mixing, and maturing over time. It is an ongoing process. Even now, new stars with yet higher heavy element content are being born, adding a new layer atop the old. The galaxy we inhabit today is the sum of all these eras. We walk under a sky of ancient and youthful stars, cosmic fossils, and fresh beacons side by side. The layered history of the Milky Way reminds us that our galaxy is a dynamic, evolving entity, and that our very existence depends on that long history of star birth and star death that built up the elements of life. We are, quite literally, children of the stars from generations long gone, inheritors of a galaxy billions of years in the making. Stars are born from the raw material of the galaxy, vast clouds of gas and dust drifting in the interstellar medium. These clouds, called giant molecular clouds, are often tens to hundreds of light years across and contain thousands of times the sun's mass in cold hydrogen gas laced with cosmic dust. In their normal state, they are dark and obscure, blotting out the stars behind them as cold silhouettes. But within them, gravity works quietly over millions of years, gathering clumps of material until, in some regions, the cloud can no longer support its own weight. A slow collapse begins. What starts as a diffuse, chilled cloud of molecules and dust begins to fragment and fall inward into denser knots. As a knot collapses, it heats up and spins faster, a newborn star in the making. Deep inside such a collapsing protostar, temperatures climb until hydrogen atoms begin to fuse into helium. When that moment arrives, a new star ignites, shining with nuclear fire. Often, not just one star forms, but dozens or hundreds. Gravity tends to create many cores from one cloud, yielding a cluster of siblings. These infant stars are initially hidden from view by their natal dust cocoons, but their radiation and stellar winds soon blow away the surrounding shrouds. When the curtains lift, we see the results: clusters of hot young stars and the remaining cloud material carved into fantastic shapes by the energy of their birth. The sites of recent star formation announce themselves through nebulae, glowing clouds of ionized gas. Massive newborn stars, often of spectral type O or B, pour out intense ultraviolet light that ionizes hydrogen in the surrounding cloud, causing it to fluoresce in pink and red hues. These regions, known as H2 regions, pronounced H2, mark the nurseries where stars have just formed. One of the nearest examples is the Orion Nebula, visible as a small fuzzy patch in the Sword of Orion. In that nebula, a cluster of hundreds of young stars, only 1 million years old or less, illuminates the gas around them, creating a glowing cloud visible even in small telescopes. Within the nebula, one can observe zones where gas is being sculpted by stellar radiation, cavities and ridges around the bright central cluster known as the trapezium. The Orion Nebula is essentially a stellar maternity ward in our cosmic neighborhood, a mere 1/300 light-years away, giving us a front-row view of star birth in action. All across the Milky Way, especially along the spiral arms, similar nurseries abound. The Eagle Nebula, for instance, contains the famous Pillars of Creation, towering columns of gas and dust several light-years tall, eroded by the fierce light and winds of nearby newborn stars. Inside those dusty pillars, new stars are gestating, protected from the harsh outside radiation until they grow strong enough to emerge. The tips of the pillars glow where infant stars within them heat and ionize the gas. Eventually, the pillars will be blown apart completely, unveiling the stellar brood they once hid. Such images capture a moment in a continuous cycle. A cloud gives birth to stars, and those stars then disperse the remaining cloud. In these stellar nurseries, the scene is often chaotic. Protostars firing off bipolar jets that punch through the surrounding gas, disks of material forming around young stars, some of which will coalesce into planetary systems, and shock fronts where winds from the most massive stars slam into the cloud. The most massive newborns also live fast and die young. Even while their smaller siblings are still forming, the heaviest may explode as supernova, blasting the region with shock waves that can trigger further collapse in nearby clouds, or, conversely, blow the remaining gas out into interstellar space. Star formation is as much a process of destruction as creation. Each generation of stars profoundly reshapes its environment. The spiral arms of our galaxy are particularly rich in these nurseries. As the density wave of an arm passes through a region, it gently squeezes molecular clouds, often giving them the nudge needed to start collapsing into stars. This is why we see strings of H2 regions tracing the spiral arms like beads on a cosmic necklace. They shine as signposts of where fresh stars are coming to life. Some arms host giant complexes with thousands of massive stars, veritable star factories pumping out clusters and associations of hot young stars. These OB associations, named for the O and B-type stars that dominate them, typically disperse after a few tens of millions of years, as their member stars drift apart, but not before contributing new stars to the galactic disk and enriching the surroundings with heavy elements when the biggest among them die. The life cycle continues. The remnants of one generation's molecular cloud can become the seeds of the next. The ashes of dead stars, their expelled gas and dust, mix back into the interstellar medium. In some cases, the shockwave from a supernova will sweep up gas in front of it, compressing it until new clumps form and new stars spark to life. In this way, a supernova can be both an end and a beginning, death leading to birth. At any given time, the Milky Way has numerous star-forming regions active. While individual star births might seem insignificant against the galaxy's vast timescales, collectively they add up. Our galaxy gives rise to a few new stars per year on average. Over millions of years, that builds entire clusters and replenishes the stellar population. Every bright blue star you see in the sky was once a protostar hidden in a nebula, and every nebula you see glowing is a promise that new stars have joined our galaxy. To us, the dark patches that divide the Milky Way's band in the sky, the great rifts of darkness, like the one that cleaves the summer Milky Way, might appear as voids. In reality, they are the cradles of creation, dense veils of dust and gas, home to embryonic stars. Given time and the right conditions, those black clouds will blossom into brilliant clusters, and the cycle will continue. The glowing nebulae and their newborn stars remind us that the Milky Way is alive and evolving, constantly turning gas into starlight. In their soft radiance, we witness the galaxy renewing itself. From the ashes of old stars and the primordial gas of the galaxy, new suns ignite, bringing light to the darkness and continuing the cosmic story of creation. The graceful spiral arms of the Milky Way might look like fixed structures, as if the stars themselves form grand, rotating tentacles. But this is an illusion born of our snapshot in time. In reality, the spiral arms are patterns, not permanent appendages. They are density waves moving through the galaxy's disk, like traffic jams along a highway or waves rolling through an ocean. The stars and gas clouds are the cars or the water flowing through the pattern, bunching up when they enter an arm and scattering as they leave. Imagine driving on a highway where an accident causes cars to slow down at a certain stretch. Cars behind catch up, and the density of cars increases at that spot, a traffic jam. After passing the bottleneck, each car speeds up again, leaving the jam. The jam itself may persist in the same general location or move slowly, even though individual cars are constantly entering and exiting it. This is analogous to how a spiral arm works. As stars and gas orbit the galactic center, they periodically encounter regions of higher density, the spiral arms. Upon entering an arm, the extra gravity of the concentrated mass slows them slightly and compresses any gas clouds. The result is a temporary pileup. That region has more stars and gas at any given moment than the surrounding space. Eventually, the stars drift out of the arm and resume a slightly faster orbit in the less crowded regions between arms. The spiral pattern, however, remains, continually renewed by new stars entering at the arm's upstream end and leaving at the downstream end. This mechanism resolves a classic conundrum known as the winding problem. The inner parts of a galaxy rotate faster than the outer parts. If the arms were made of the same stars all the time, like paint on a spinning wheel, they would wind tighter and tighter around the center with each rotation, and after a few galactic orbits they'd become unrecognizably tangled. But real galaxies do not show such wound-up arms. The Milky Way's arms remain relatively coherent. Density wave theory explains this. The arms are not fixed groups of specific stars. They are more like a traffic pattern that persists, even though individual stars, creating the pattern change over time. Another analogy is waves in the ocean. Consider a wave traveling through water. Water molecules mainly bob up and down. They don't move far with the wave. A leaf on the water might ride the wave up and then down, barely advancing toward shore. Similarly, a star rides up into the higher density of a spiral arm and then back down out of it, while the spiral wave itself propagates around the galaxy. The arm is a region where stars and gas spend a bit more time than average, making it denser and thus visible as a collective feature. These spiral density waves have profound effects on the gas in the disk. As a gas cloud enters an arm, the slight slowdown and compression can trigger the cloud to collapse and form new stars. Thus, the arms are marked by bright newborn star clusters and glowing nebulae. Paradoxically, the massive blue stars that light the arms live so briefly, only a few million years, that they die before moving far from where they were born. So the spiral arm is continually illuminated by short-lived stars born within it, stars that burn out before ever escaping it. In this way, the arm keeps a steady supply of luminous stars, while older, longer-lived stars, like the Sun, drift out and populate the rest of the disk. This is why the spiral arms stand out. They are outlined by fresh, brilliant stars and clusters that act like cosmic fairy lights along a winding path. The Milky Way's spiral arms are not perfectly symmetric or constant. They can split, branch, or be influenced by interactions with satellite galaxies or the rotation of the central bar. Computer simulations show that spiral patterns can form, dissolve, and reform over billions of years. But at present, our galaxy has a well-defined spiral structure with several major arm segments. The density wave pattern rotates slowly, taking perhaps a few 100 million years for one full turn around the center, slower than the orbital speed of most stars. This means stars are constantly overtaking the wave pattern. For example, our Sun, moving faster than the pattern, weaves in and out of spiral arms over time. Indeed, it's currently in a minor spur rather than a major arm. Understanding that the arms are dynamic patterns helps us appreciate the Milky Way as a living galaxy. The arms are not material limbs flung out in a whirl. They are the visible imprint of waves of density and star formation moving through the disk. In them, we see the choreography of billions of stars responding collectively to gravity's gentle organizing force. Each swing of the pattern triggers new star birth, maintains the galaxy's graceful form, and adds to its enduring beauty. When we picture the Milky Way's majestic arms, we should remember they are like moving ripples on a sea of stars, gathering stars for a time, then releasing them, sustained by the ongoing rhythms of cosmic traffic. The spiral arms truly are waves of change sweeping through our galaxy, preserving the spiral design even as the cast of stars continually changes. Between the stars of the Milky Way lies a diffuse medium of gas and dust, the stuff from which stars form and to which they return when they die. This interstellar medium may appear invisible and tenuous, but it's a vital component of the galaxy. If you drifted in the space between stars, you would not be an absolute vacuum. On average, each cubic centimeter of space around us contains about one atom, typically hydrogen. In some regions, the density is far lower, in cavities carved by past supernova explosions, and in others, densities climb to thousands or millions of atoms per cubic centimeter inside cold nebulae. The interstellar medium is a patchwork of phases: cold, dense clouds where molecules form, warm, diffuse gas filling much of the disk, and hot, ionized plasma blown by stellar winds and supernovae, reaching millions of degrees and expanding far into the halo. Though extremely thin by earthly standards, even the densest interstellar cloud is emptier than the best vacuum we can create. The sheer volume of space it occupies makes its total mass significant. The combined mass of gas and dust in the Milky Way's disk is on the order of tens of billions of suns, and surrounding the galaxy is an even larger reservoir, a vast halo of hot gas detected in X-rays, extending hundreds of thousands of light years out. Observations suggest this halo contains an amount of matter comparable to all the stars in the galaxy. This halo gas, heated to millions of degrees, is so thin we detect it only by its faint X-ray glow and how it absorbs certain wavelengths from distant sources. It likely represents the Milky Way's share of cosmic matter that didn't collapse into the disk, a gigantic atmosphere for our galaxy, enriched by outflows from countless past supernovae. Within the disk, the interstellar medium makes itself known in various ways. We see glowing nebulae where gas is ionized by starlight. We also see dark nebulae, clouds of dust and molecular gas that block light, appearing as black voids or silhouettes against the starry background. The great rift that splits the Milky Way's band, clearly visible on a summer night from a dark location, is caused by such dust clouds obscuring light from distant stars in the galactic plane. These dust-laden clouds are not just obstacles to our view, they are the nurseries of future stars. The dust itself consists of tiny solid grains, microscopic particles of silicates, carbon compounds, ices, and metals. These grains originated in the cool atmospheres of old giant stars and in supernova explosions, then were blown into space. Over time, uncountable grains aggregate into clouds, soak up starlight, especially blue light, which they scatter more effectively, leaving transmitted light reddened, and provide surfaces on which complex chemistry can occur. In the shelter of dense clouds, dust grains catalyze molecule formation. Hydrogen atoms join to form H2, and more complex molecules assemble on grain surfaces. As a result, molecular clouds are rich chemical laboratories. Astronomers have detected over 200 molecules in interstellar clouds, from simple carbon monoxide and water to organic molecules like formaldehyde, alcohols, and even precursors of amino acids. Within these clouds, ingredients for life, water, organic compounds, are being synthesized and blended into the material that will form new stars and planets. Every star system, including our own, was born from such a chemically enriched cloud, inheriting a brew of elements and compounds forged by earlier stars and interstellar chemistry. Where there is gas and dust, there are also magnetic fields and cosmic rays. The Milky Way's interstellar medium is threaded by invisible magnetic field lines that influence the motion of charged particles and the collapse of clouds. Cosmic rays, high-energy particles, mostly protons and atomic nuclei, accelerated by supernova shocks and other energetic events, zip through the galaxy at near light speed, permeating the interstellar medium. Together, cosmic rays and magnetic fields exert pressure on gas and can affect how clouds condense or disperse. In a sense, the space between stars is alive with activity. Not a silent void, but a dynamic environment where forces push and pull and energy flows in many forms. One of the most perceptible effects of the interstellar medium is the dimming and reddening of starlight. When light from distant stars passes through an intervening dust cloud, the dust absorbs and scatters the shorter, bluer wavelengths more than the longer, redder wavelengths. The star thus appears redder and fainter, an effect known as interstellar extinction. This is why the galaxy's core, though packed with stars, is hidden from view in visible light. Dust along our line of sight obscures it. Only by observing in infrared, radio, and other dust-penetrating wavelengths can we map the center and far side of the Milky Way. In effect, the interstellar medium both gives and takes away. It creates beautiful nebulae and new stars, but also veils parts of our galaxy from us. Despite its elusiveness, the interstellar medium is crucial to the Milky Way's ecosystem. It's the reservoir of matter for new star formation and the repository of matter returned by dying stars. A star like the Sun will eventually blow off its outer layers, enriching the ISM with freshly forged elements like carbon and nitrogen. More dramatically, a supernova will eject its guts, heavy elements like iron, silicon, and calcium, into space, seeding the surroundings. Those elements then drift through the medium for eons, until gravity gathers that gas into new clouds and new stars, which will have higher amounts of heavy elements than the generation before. In this way, the interstellar medium is the conveyor belt of galactic evolution, cycling material from stars to space and back into stars. Far from being an empty void, the space between stars is a complex tapestry of filaments, bubbles, and clouds. In some places, it's a hot, X-ray emitting plasma from recent violent events. In others, it's a cold, quiescent womb where starlight has yet to penetrate. It connects all parts of the galaxy. The winds from one star can eventually reach the clouds that birth another, and the enrichment from long-dead stars finds its way into newborn planetary systems. When you gaze up at the Milky Way and notice its dark lanes and milky glow, you are indirectly seeing the interstellar medium, the dust causing darkness and the integrated light of countless distant stars diffused by intervening gas. The interstellar medium is the breath of our galaxy, the ethereal bridge between stars, carrying on the endless cycle of cosmic renewal. Encircling the Milky Way, far outside the bright disk, is a diffuse halo of ancient stars, a stellar halo that serves as a living fossil of the galaxy's early days. Within this halo orbit, the globular clusters, which are among the oldest surviving structures in the galaxy. Globular clusters are dense, spherical swarms of stars containing tens of thousands to millions of stars packed into a ball only a few hundred light-years across. About 150 such clusters are known around our galaxy, with likely a few more hidden in the far reaches. They are cosmic old folks' homes, filled with stars that formed together at the dawn of the Milky Way, over 12 billion years ago. Imagine a globular cluster as a glittering globe of stars. If you look through a telescope at one, say, the Great Cluster in Hercules, M13, or Omega Centauri in the southern sky, you see a concentrated blaze of starlight, countless diamond-like points crowding toward the center. In their cores, stars are so tightly packed that the average distance between neighbors can be less than a light year. For context, our sun's nearest neighbor is over 4 light-years away. If you lived on a planet inside a globular cluster, your night sky would be carpeted with thousands of brilliant stars, many far closer and brighter than any we see from Earth. The clusters move like satellites around the galaxy, often on elongated or inclined orbits that carry them high above and below the galactic plane. They pay little heed to the spiral arms or the disk. Instead, they trace out the galaxy's spherical gravitational potential. The stars within globular clusters have distinctive fingerprints. They tend to be extremely metal-poor, even compared to typical halo stars, which indicates their great antiquity. In many globulars, virtually all the stars formed at almost the same time. The whole cluster is a coeval family, born from one primordial cloud, making them useful as benchmarks for stellar ages. A few clusters show evidence of multiple episodes of star formation, but even those later generations are still extremely old, likely forming only a few 100 million years after the first. In short, globular clusters preserve the conditions of the early Milky Way, like insects in amber, each cluster a time capsule from an epoch when our galaxy was just coming together. The distribution of globular clusters was the clue that first revealed the galaxy's true expanse. Early in the 20th century, astronomers noticed globular clusters are not centered on the Sun, but roughly around Sagittarius. This revelation helped establish that the Sun is far from the galactic center. Most globulars lie in a spherical arrangement about the galactic core, with the highest concentration toward the center. About 90% orbit within 100,000 light-years of the center. However, a few renegade clusters roam even farther out. For instance, clusters like Palomar 4 and AM1 are well over 200,000 light-years away, on the outskirts of the halo. These remote clusters push the boundaries of the Milky Way's gravitational reach. Where did these clusters come from? They likely represent some of the building blocks from which the Milky Way grew. In the galaxy's infancy, proto-galactic fragments and smaller dwarf galaxies merged to form the larger system, and those smaller pieces often produced globular clusters during their own star formation bursts. Some globulars might be the cores of dwarf galaxies that the Milky Way tore apart long ago, tightly bound remnants that survived the tidal destruction. A compelling example is Omega Centauri, the brightest globular cluster in the sky, visible to the naked eye in the south as a faint smudge. Omega Centauri is unusually massive and has stars of different ages, suggesting it wasn't formed in one go. Astronomers suspect it's the leftover nucleus of a small galaxy that the Milky Way shredded billions of years past. What remains is its central star cluster, now orbiting as a globular. This hints that the halo is partly built from the remains of other galaxies, a theme we'll explore further with galactic cannibalism. Beyond the clusters, the halo contains solitary stars, lone wanderers, mostly old and on eccentric orbits. These halo stars either date from the Milky Way's initial formation or were stripped from smaller galaxies that strayed too close. The halo also hosts ghostly stellar streams, long filaments of stars stretched across the sky, which are the shredded remnants of former globular clusters or dwarf galaxies currently being assimilated. For example, astronomers have mapped the Sagittarius Stream, a ribbon of stars pulled from the Sagittarius dwarf elliptical galaxy, a satellite now merging with the Milky Way. Such streams lace the halo like wisps, proving that the Milky Way's growth is ongoing. In effect, the globular clusters and halo stars form the ancient outermost layer of our galaxy. They're guardians of memory, orbiting the center with patience. When we peer at a globular cluster through a telescope, we're seeing a population of stars that has witnessed our galaxy's entire life, from near the beginning until now. The halo may be faint to our eyes, giving off little light compared to the bright disk, but it's a crucial part of the Milky Way's structure, enclosing it in a spherical embrace. It also provides, along with dark matter, a gravitational scaffold that holds the galaxy together. The globular clusters, sparkling like far-flung beacons, and the sparse halo stars paint a picture of a galaxy assembled over time, capturing and merging smaller systems. They remind us that our Milky Way, for all its grandeur, is itself a product of countless mergers in the deep past. High above and below the galactic plane, in the dim halo, the globular clusters orbit undisturbed for eons, like ancient sentinels. Their stars will eventually die and fade, but the clusters can endure for many billions of years more. They'll likely be among the last recognizable structures of our galaxy, even after the spiral arms dissolve and the Milky Way has merged into something new. In these clusters, one senses the deep time and resilience of the galaxy. They are the Milky Way's oldest residents, faithfully circling the galactic center as they have since nearly the dawn of time, carrying the story of the galaxy's birth in their dense, starry realms. Yet, for all the stars, gas, and dust we see, the Milky Way has an even more massive component that we cannot see at all: dark matter. This is one of the great mysteries in astronomy today. Observations of our galaxy and others suggest about 85% of the Milky Way's mass is dark matter, a substance that does not emit, absorb, or reflect light. It's invisible in every wavelength we can observe, earning the name dark. We know of its existence only by its gravitational tug on visible matter. Dark matter forms a vast, roughly spherical halo enveloping the Milky Way. It extends well beyond the edge of the visible galaxy, perhaps several 100,000 light-years out. Every star, cluster, and cloud in our galaxy is moving in a gravitational field dominated by this unseen mass. The first hints of dark matter in the Milky Way came from studying how stars and gas move in the galaxy's outer regions. Based on visible material alone, you'd expect stars farther out to orbit more slowly, like planets farther from the Sun move slower due to weaker gravity. But to astronomers' surprise, stars in the distant outskirts of the Milky Way were moving just as fast as stars closer in. Something extra was providing the gravity to keep those fast-moving outer stars bound to the galaxy. If the mass of the galaxy dropped off where the light does, those outer stars and gas clouds should have flown off into space. The fact that they remain in orbit implies a tremendous amount of unseen matter extending far out, exerting gravitational pull. Similar findings in other galaxies and galaxy clusters confirmed that a huge portion of matter is invisible. Thus, we infer the Milky Way is surrounded by an enormous dark matter halo. Unlike the halo of stars, which we can glimpse in globular clusters and streams, the dark halo emits no light and is far more massive. Picture the galaxy's visible parts, the bright disk and central bulge, as a little frisbee and a yolk, respectively, nested inside a vast, diffuse ball of transparent material, far larger and heavier. That's our situation. The dark matter halo not only extends beyond the stellar halo, it likely outweighs all the stars by a factor of 5 or more. The Milky Way's total mass is roughly 1 trillion times the Sun's mass, but stars, gas, and dust make up only a small fraction of that. The rest is dark matter. What is this dark matter? We aren't sure. It's not made of the same kind of particles as we are, the protons, neutrons, electrons of normal atoms. It's not simply a bunch of faint stars or rogue planets or black holes. Those ordinary possibilities don't add up to nearly enough mass. The leading idea is that dark matter consists of some new type of particle, one that interacts so weakly with normal matter and light that it hardly ever collides or emits radiation. These hypothetical particles pervade the halo, streaming even through Earth and our bodies unnoticed, except for their gravity. Physicists have built sensitive underground experiments to try to catch a dark matter particle interacting with normal matter, but so far, none has been definitively detected. The true nature of dark matter remains elusive, making it a profound puzzle at the intersection of cosmology and particle physics. Nevertheless, dark matter's gravitational effects are well documented. It explains the flat rotation curve of the galaxy, the roughly constant orbital speeds of stars at various distances from the center. If mass were concentrated mostly in the inner parts, where the light is, orbital speeds should drop off in the outer galaxy, much as planets farther from the Sun orbit slower. But they don't drop, they stay high. That flat rotation curve tells us mass continues to increase with radius, far beyond the visible disk, consistent with a massive dark halo. Dark matter also helps hold together the loosely bound outer structures. Dwarf satellite galaxies and distant globular clusters orbit faster than they would if only visible matter existed. But with the dark matter's extra gravity, their orbits make sense. Furthermore, the presence of dark matter in the early universe allowed galaxies like ours to form. Dark matter clumped first, since it doesn't feel pressure or light, providing gravitational wells into which normal gas later fell to form stars and galaxies. In this sense, dark matter is like the cosmic scaffolding upon which luminous structures, like the Milky Way, were built. There are other clues of dark matter in our galaxy. One is gravitational lensing. Light from distant stars or galaxies is subtly deflected as it passes through the Milky Way, bending around unseen mass. By mapping these distortions, astronomers can infer the distribution of all mass, visible and dark, in our galaxy. These studies support an extended massive halo that far outweighs the visible portions. Another clue comes from the motions of satellite galaxies. Dozens of dwarfs orbit the Milky Way, like the Magellanic Clouds and others, and their movements suggest they feel the pull of far more mass than we can see directly. All lines of evidence indicate dark matter is real and forms the majority of our galaxy's mass. Yet, because it neither shines nor blocks light, one could drift through a dark matter cloud and never notice it. It's a cosmic shadow, shaping the galaxy, governing the motions of stars and gas, but invisible. Its presence forces us to confront the humbling fact that the stars are nebulae, and by extension we, who are made of that same ordinary matter, are a minority of the Milky Way's mass. The bulk of our galaxy is something fundamentally alien to our senses. This great unknown adds an aura of mystery to the Milky Way. As we map the galaxy in increasing detail, we outline dark matter's influence, but can't yet pinpoint its nature. Perhaps one day, physics will reveal what dark matter truly is. Until then, it remains a shadowy halo, the Milky Way's unseen frame, a colossal silent partner holding our galactic home together. We live in the light of stars and nebulae, but we are also encompassed by a dark gravitational sea. One of the strongest pieces of evidence for dark matter came from charting the Milky Way's rotation curve. How fast objects orbit the center at different distances. If we could measure orbital speeds from the inner galaxy out to the far outskirts, classical physics predicts a certain pattern. Near the center, speeds rise with increasing enclosed mass. But beyond most of the mass, speeds should fall off. Like planets farther from the Sun orbit slower, because most of the Sun's mass is behind them. In other words, we expected a peak around the inner disk, then a steady decline in orbital velocity with distance, reflecting a drop-off in mass. Measuring the Milky Way's rotation from within is tricky, but astronomers devised ingenious methods. They use the Doppler shift of spectral lines, especially the 21-centimeter radio line of neutral hydrogen, to gauge how fast gas is moving along our line of sight in different parts of the galaxy. By mapping these velocities and using geometry, they infer orbital speeds at various radii. The Sun, for example, orbits at about 220 kilometers at 26,000 light-years out. The surprise came when scientists extended measurements further. Instead of dropping, rotation speeds stayed high, roughly constant around 200–240 kilometers, far beyond the visible edge of the disk. Gas clouds orbiting 50,000 or 60,000 light-years from the center moved nearly as fast as gas 10,000 light-years out. This flat rotation curve defied expectations. If the Milky Way's mass were mostly in the visible stars and nebulae, the orbital speed at 50,000 light-years should be much lower than at 25,000 light-years, just as Neptune orbits slower than Earth. The fact it isn't means the mass within 50,000 light-years is far greater than the visible stars alone provide. In essence, as you go outward, you keep finding more gravitational pull than anticipated, as if an unseen bulk of matter extends into the darkness. The flat rotation curve suggests the Milky Way's mass keeps growing with radius well beyond the visible disk. Eventually, at some very large radius, it must taper, but measurements out to the farthest gas, and even using the motions of satellite galaxies, show the mass enclosed is still rising even out to about 100,000 light-years. This matches perfectly with the idea of a massive dark matter halo. Historically, this realization dawned by the mid-20th century as radio astronomers extended rotation measurements and astronomers studied other galaxies. By the late 1900s, it was clear many spirals have flat rotation curves. Our Milky Way, being harder to map from within, nonetheless showed the same behavior. The term missing mass was used before dark matter became standard, but the implication was the same. Something invisible was contributing most of the gravity. The flatness of our galaxy's rotation curve is a cornerstone of the dark matter hypothesis, direct evidence that most of the Milky Way's mass is not where the light is. To put numbers on it, at the Sun's orbit, 26,000 Li, the orbital velocity is about 220 kilometers. If only the mass inside the Sun's orbit, mostly the bulge and part of the disk, were pulling on us, then by 50,000 pounds lie out, one would predict velocities to drop significantly, like to maybe 150 kmol. But observations show it remains 220 pounds/kilometers, sometimes a bit higher, at 50,000 pounds/Li, 60,000 pounds/Li, and beyond. This fact demands that a lot of additional mass lies farther out. In a sense, the stars and gas we see are riding on a massive merry-go-round whose full extent is far larger than the lit-up platform. We have refined the rotation curve with various traces: hydrogen gas via its radio emission, carbon monoxide clouds via millimeter wave emission, and even certain star populations at known distances. All agree, the outer galaxy rotates faster than expected from visible matter alone. This consistent behavior strongly supports an extended dark matter halo. Alternative theories, like modifying gravity, have been proposed, but those struggle to explain all observations, especially on scales of clusters and cosmology. Thus, the flat rotation curve stands as a key clue that dark matter dominates our galaxy's mass budget. For our Milky Way, the rotation curve flattens already within a few thousand light-years of the center and stays flat, with minor wiggles due to spiral arm mass concentrations, as far out as we can measure. The motion of distant satellites suggests it stays flat or only gently declines even at extreme radii. This indicates the dark matter halo is very extended. We're not sure exactly where it ends, perhaps hundreds of thousands of light-years out, where the influence of neighboring Andromeda's halo might start to compete. In summary, the unexpectedly high, flat rotation velocities in the outer Milky Way were a pivotal clue that most of the galaxy's mass is invisible. The luminous spiral that we see is effectively the tip of an iceberg. Beneath it, or around it, lies the bulk of matter that controls the dance of stars. Discovering the Milky Way's flat rotation curve transformed our understanding, revealing that the shining stars do not tell the whole story of what's there. Instead, the stars move under the gravitational guidance of a vast, dark structure, an unseen halo that extends far beyond the starry disk. The steady rotation of the Milky Way, even in its far outskirts, is the signature of that hidden mass. A gentle but persistent whisper in the motions of the stars, telling us that something enormous yet invisible shares our galactic home. The Milky Way has not grown in isolation. Over its lifetime, it has acted as a cosmic predator, consuming smaller galaxies that wandered too close, a process astronomers bluntly call galactic cannibalism. Our galaxy, like others of its size, is the product of many mergers and accretions. In its early youth, the Milky Way likely amalgamated several protogalaxies, each bringing its own stars and clusters, hence the abundance of ancient clusters in our halo. Even in more recent times, the Milky Way continues to snack on smaller neighbors. Evidence of past mergers is written in the stars of the halo and even in the disk. One example became clear with data from the Gaia Space Observatory. A large population of halo stars moves in a distinctive pattern, as if they originated from a single disrupted system. Their motions and compositions suggest that around 10 billion years ago, a dwarf galaxy, several times more massive than any of our current satellites, plunged into the Milky Way and was torn apart. This event, sometimes nicknamed Gaia Enceladus or the Gaia sausage by scientists, contributed a substantial fraction of our stellar halo and even puffed up the disk, creating the thick disk of older stars. The debris of that ancient galaxy now orbits within us, its stars thoroughly mixed into the Milky Way's population, but still betraying a common origin in their paths and chemistry. Our galaxy's cannibalistic habits are ongoing. We currently observe at least 2 dwarf galaxies in the process of being devoured. The most prominent is the Sagittarius Dwarf Elliptical Galaxy, a small satellite galaxy that has already had multiple close encounters with the Milky Way. Over the past few billion years, the Milky Way's strong tides have stretched and ripped Sagittarius apart, peeling off streams of its stars. These stars now form a sprawling stellar stream that wraps around the Milky Way like a gossamer ribbon. Eventually, the remaining core of the Sagittarius dwarf will dissolve completely, its stars assimilated into our halo and disk. We are witnessing the slow destruction of a galaxy by our own. Another example is the Canis Major overdensity, which some interpret as the remnants of a dwarf galaxy being consumed by the Milky Way from the direction of Canis Major. It too may have donated stars and a few globular clusters to our halo. Indeed, some globular clusters with unusual properties like M54 are thought to have originally belonged to Sagittarius or other devoured galaxies. These accretion events show that some portion of our clusters and halo stars originally formed outside the Milky Way and were later captured. The halo is like a quilt stitched together from many ancestral galaxies. In addition to these past and current meals, the Milky Way keeps a retinue of satellite galaxies orbiting it, and some of these are destined to be future snacks. The Large Magellanic Cloud, LMC, and Small Magellanic Cloud, SMC, visible to the unaided eye from the southern hemisphere as blurry patches, are our most massive present satellites, each containing billions of stars. They orbit each other and the Milky Way, and they're interacting with both. A stream of hydrogen gas, the Magellanic Stream, arcs behind them, torn out by tidal forces and ram pressure as they move through the Milky Way's halo. Eventually, perhaps a few billion years from now, the Magellanic Clouds too will merge with the Milky Way, their stars becoming part of the larger galaxy and their gas likely triggering new star formation in our disk. Our galaxy has at least a few dozen known satellites, with new ultrafaint dwarfs still being discovered, most extremely small. These tiny galaxies often have only a few million stars each and are heavily dominated by dark matter. They swarm around the Milky Way like minnows around a whale. Some will remain in orbit for a long time, but others will gradually spiral in and dissolve. Indeed, the halo contains multiple stellar streams beyond the Sagittarius stream, such as the Virgo stellar stream, the Orphan stream, and others, which are the trails of stars left by past mergers or by satellites currently being disrupted. Each stream is like a scar in the halo, marking where a smaller galaxy was torn apart along its orbit. Modern surveys like SDSS and Gaia have revealed these ethereal structures, making it clear the Milky Way's halo is a dynamic environment, still accreting its neighbors. Galactic cannibalism is a common theme in the universe. Big galaxies grow by eating small ones. In fact, our local group of galaxies is dominated by two giants, the Milky Way and Andromeda. And Andromeda has likewise been feasting on dwarfs. A large halo structure in Andromeda hints at it. In the grand future, the Milky Way's next major meal won't be a dwarf, but a near equal, the Andromeda galaxy itself. The Milky Way's cannibalistic career will culminate in a titanic merger with Andromeda in a few billion years. That impending collision is a story in its own right, but it underscores that no galaxy is an island unto itself forever. Gravity weaves galaxies together, building larger ones from smaller pieces. The Milky Way's current grandeur is partly the spoils of its past devouring of others. And even as we admire our galaxy's light, we should acknowledge those other star systems whose light was subsumed into ours. Their stars, now citizens of the Milky Way, continue to shine on, telling of the galactic lives their original homes once led. Though it sounds violent, galactic cannibalism is a slow dance by human standards. The Sagittarius dwarf, for example, has been merging for billions of years, its stars gradually dispersing. When the Magellanic clouds begin to merge, it will unfold over similarly long timescales, creating spectacular streams and perhaps igniting bursts of star formation. We living beings on Earth likely won't feel these events directly, but we can detect and trace them across the sky. In this way, the Milky Way is both a single entity and a composite of many, an amalgamation forged by gravity's relentless mergers. Each absorbed galaxy adds to the richness of our own, new stars, new clusters, sometimes subtle ripples in our galaxy's structure. Standing on the edge of the galactic disk, we might imagine the ghostly remains of these consumed galaxies encircling us. Indeed, in the halo above, some of the stars you see might once have belonged to a completely different galaxy before joining ours. The story of the Milky Way is, in part, the story of many smaller galaxies that came together. As our galaxy continues its cosmic dining, it reminds us that even galaxies are not static. They grow, change shape, and exchange matter, all part of the ongoing evolution of structure in the universe. In the Milky Way's majestic glow lies the light of many ancestral worlds, now united in a single, larger family. The next great family reunion will happen when we meet Andromeda, heralding a new chapter in this cosmic tale. Our galaxy's future holds a dramatic event, a collision with the Andromeda galaxy, our giant neighbor. Andromeda, also known as M31, is currently about 2.5 million light-years away, visible as a faint smudge in a dark sky. It is the Milky Way's sister spiral in the local group, with perhaps as many stars as our galaxy, or more. For a long time, we've known Andromeda is moving toward us. Its light is blue-shifted, indicating approach at around 110 km/s. Project this motion billions of years forward, and the conclusion is unavoidable. The Milky Way and Andromeda are on a collision course. It's not a smash like two billiard balls. Galaxies are mostly empty space, so when they collide, their stars almost all sail past each other. But the gravitational interaction will be profound. Roughly 4 billion years from now, give or take hundreds of millions of years, the disks of the two galaxies will begin to interpenetrate. For any beings around at that distant time, the night sky will change spectacularly. Andromeda will grow from a faint patch to a large whirling form spanning the sky, and then to a chaotic blaze of stars as the galaxies first clash. During the initial pass, the Milky Way's and Andromeda's disks will be badly distorted. Tidal forces will fling out long streamers of stars, tidal tails arcing far into space. The neat spiral arms will tangle and break. Some stars may be thrown into intergalactic space, while others shifted into new orbits. Clouds of gas in both galaxies will slam into each other, compressing and igniting a frenzy of new star formation. A cosmic fireworks display lighting up the merging galaxies with countless young, massive stars, and later, supernovae. After that first collision, the two galaxies will likely swing apart somewhat, trailing starry tails, then be drawn back together by gravity. They'll oscillate and intermix over a couple more billion years, their cores eventually coalescing and settling into one unified system by around 6-7 billion years from now. By the end of this titanic merger, the Milky Way and Andromeda as we know them will be gone, replaced by a single larger galaxy. Astronomers often dub this future galaxy Milkomeda. It will likely be an elliptical galaxy or a giant fuzzy disk. The exact outcome depends on details like the collision's angles and gas content, but the elegant spiral structures of both will probably be disrupted into a more amorphous form. For any hypothetical observers within the galaxies during the merger, perhaps far future descendants of humanity or other life forms, it wouldn't necessarily be catastrophic in terms of star collisions. The distances between stars are so vast that direct stellar crashes are extremely unlikely. However, the night sky would be unlike anything humans have seen. As Andromeda merges with the Milky Way, the sky could be filled with swirling rivers of stars, brilliant nebulae from colliding gas clouds, and bursts of light from clusters forming and supernovae exploding. Over millions of years, constellations would warp beyond recognition as whole star systems shift. If Earth still exists, then, though by that time the Sun will be in its red giant phase, possibly rendering Earth uninhabitable, the Sun itself might be flung into a different region of the new merged galaxy. It's unlikely the Sun would be ejected entirely, but it could end up further out in the merged system, or perhaps closer to the core, depending on tidal forces. One certain outcome of the merger is the interaction of the two supermassive black holes. The Milky Way's central black hole, a few million solar masses, and Andromeda's, perhaps 10 times more massive, will spiral toward each other as the galaxies merge. Eventually, these giants will coalesce into an even more massive black hole at the heart of the new galaxy, releasing a burst of energy in gravitational waves as they do. That final union will occur after the initial collision, once dynamical friction has brought the black holes together. A dramatic, but invisible to human senses, event, except maybe to advanced beings who could detect such gravitational ripples. From a cosmic perspective, the Milky Way-Andromeda collision will mark the beginning of a new era in the local group. Right now, the local group has our Milky Way, Andromeda, the Triangulum Galaxy, M33, and dozens of dwarfs. After we merge with Andromeda, M33 might later fall in as well. Some models suggest it will. Ultimately, many billions of years in the future, what remains may be a single giant galaxy where once there were many. The local group would have effectively condensed into one galaxy. The night sky of that far future merged galaxy, to any observers within it or outside of it, would be dominated by one huge combined galactic glow instead of the distinct band of the Milky Way. For any creatures experiencing the early stages of the merger, the spectacle would be awe-inspiring. In the run-up to collision, Andromeda would loom larger each eon. At some point, perhaps multiple Milky bands, ours and Andromeda's, might crisscross the sky. During the merger, new stars and nebulae would make the heavens dazzlingly busy. However, these changes occur over time spans far longer than a human life. They'd be noticed by civilizations rather than individuals, unless technology allowed near-immortal observers or time-lapse perceptions. After the fireworks, the combined galaxy will eventually calm down. The burst of new star formation will subside as the gas is used up or heated. The merged galaxy will become redder as young blue stars die and not many new ones replace them, since much gas was either turned into stars or blown away. It could resemble the giant elliptical galaxies we see in clusters, large, rounded systems with little cool gas or new stars. That could be the ultimate fate of the Milky Way, to become part of a different kind of galaxy entirely, shaped by a union with Andromeda. While this future collision sounds apocalyptic, on the scale of solar systems, it may be more of a slow rearrangement than a violent crash. Still, it's awe-inspiring and perhaps a bit unsettling to realize that the familiar night sky is temporary. The Milky Way's current form, its spiral arms, its barred center, its solitary majesty in our sky, will all be transformed. Our galaxy is destined to change dramatically. The silver river of the Milky Way will eventually merge with Andromeda's great spiral, and together they'll form a new, larger galaxy. Galaxies, like clouds or living creatures, have life cycles. They are born, they evolve, and they can join to create new entities. The Milky Way's rendezvous with Andromeda will be one of the defining episodes of its life story, and though none of us will witness it, we can predict and imagine this distant spectacle as a final grand chapter, or perhaps a new beginning, in the saga of our galactic home. In that far future, if some sentient being looks up at the sky from a world in the merged galaxy, they might see not a narrow, milky band, but an all-encompassing hazy glow, the combined light of two galaxies, now one. And where we now speak of the Milky Way with its rich history, they will speak of an even larger cosmic city of stars, born from the union of two great spirals that danced and became one. For most of human history, our perception of the Milky Way was limited to what our eyes can see, visible starlight, and the dark dust lanes that block it. But the galaxy emits and absorbs a broad spectrum of radiation beyond the optical, and over the last century, we've learned to observe the Milky Way in these other colors of light. Each reveals a different facet of our galaxy, allowing us a more complete picture than visible light alone could ever provide. Radio waves were the first window beyond the optical to open. In the early 1930s, radio emission was discovered coming from the direction of the galactic center. Since then, radio astronomy has mapped the Milky Way in great detail. One of the most important radio emissions is the 21-centimeter line of neutral hydrogen. By surveying this line across the sky, astronomers in the mid-20th century traced the spiral arms and measured the galaxy's rotation, even on the far side, which optical astronomy can't see due to dust. Thus, we charted the distribution of hydrogen gas throughout the Milky Way. Radio waves pierce the dust that blinds us in visible light. In radio maps, the Milky Way's disk is filled with swirling arms of hydrogen gas, extending well beyond the visible starry disk. Radio telescopes also discovered a strong radio source at the galaxy's center, later identified with the black hole, and detected the faint glow of myriad supernova remnants, expanding shells of ionized gas, and other emissions caused by cosmic rays spiraling in magnetic fields. In radio, the Milky Way is a mix of diffuse hum and bright spots. The diffuse radio hum comes from electrons caught in the galaxy's magnetic field, and the bright spots correspond to regions like the galactic center, supernova remnants, e.g. Cassiopeia A, and star-forming zones, where ionized gas abounds. Moving to microwave and millimeter wavelengths, we can map molecular gas. Telescopes tuned to millimeter waves detect rotational transitions of molecules such as carbon monoxide, CO, which traces molecular hydrogen, H2. Using these, astronomers mapped giant molecular clouds, the cold, dense starbirth nurseries, across the Milky Way. These maps show concentrations of molecular clouds along the spiral arms and toward the center, complementing the 21 centimeter hydrogen maps. Together, they give a 3D distribution of the galaxy's interstellar gas. Additionally, microwave observations by satellites like COBE and Planck have given full sky images of the Milky Way's dust emission. The dust that appears dark in visible light actually glows faintly in the far infrared and microwave, as it's warmed to only tens of degrees above absolute zero by starlight. These maps show the Milky Way's plane as a bright band of thermal emission, highlighting cold dust in dense clouds. Before focusing on the cosmic microwave background, the Planck satellite produced some of the best microwave images of the sky, dominated by our galaxy's swirling dust and gas filaments. Infrared light gives another penetrating view. Infrared has longer wavelengths than visible, so it is less impeded by dust. Infrared observations, especially in the near-infrared, a few microns, can see stars on the far side of the galaxy that are completely hidden to optical telescopes. The first full-sky infrared surveys, like the IRAS satellite in the 1980s and the COBE satellite's Derby instrument, later the 2-mass survey in the 1990s, transformed our view of the inner Milky Way. Suddenly, the central bulge and bar came into clear focus, since their stars shine through the dust in infrared. What was a mysterious dark gap in visible light became a bright, resolved structure in infrared. The mid-infrared reveals warm dust and complex molecules, like PAHs, polycyclic aromatic hydrocarbons, in star-forming regions, outlining the spiral arms in a diffuse glow of warm dust. Modern infrared space telescopes, such as Spitzer and the newer James Webb, have captured stunning images of star-forming nebulae and the galactic center in infrared, peering through veils of dust to show star clusters crowded around the central black hole or embedded in their birth clouds. Thanks to infrared astronomy, we know the Milky Way is a barred spiral. The bar was hard to discern in optical surveys due to dust, but infrared surveys left no doubt of its presence and helped measure its size and orientation. Ultraviolet light is mostly absorbed by dust, so the Milky Way's UV view is patchy. However, UV observations, like with the Galactic satellite, highlight hot, young stars and pinpoint where recent star formation has occurred. The UV sky of the Milky Way is dominated by the nearest OB associations and the glow of hot stars in spiral arms relatively close by, since distant UV emission is largely snuffed out by dust. It doesn't easily probe through the entire disk, but it's excellent for identifying local regions of active starbirth. For instance, Galactic images show the ultraviolet shine of the Orion Arm's massive stars and of star-forming rings and regions in some parts of the galaxy. X-rays let us see high-energy processes and very hot gas in the Milky Way. With X-ray observatories like Rosat, Chandra, XMM Newton, astronomers have mapped a diffuse X-ray background emanating from hot plasma in our galaxy's halo, and from the combined emission of many faint X-ray sources. The galactic center region in X-rays is especially dramatic. Images reveal a glow of multi-million degree gas filling the inner few hundred light years, likely fed by supernova explosions and possibly past outbursts of the central black hole. X-ray telescopes have also catalogued numerous X-ray point sources in the Milky Way. These are mostly neutron stars and black holes in binary systems, siphoning gas from companion stars and emitting powerful X-rays. Such objects are invisible or inconspicuous in optical light, but in X-rays they shine intensely. For example, the famous system Cygnus X1, containing a black hole, is one of the brightest X-ray sources in the sky. X-ray maps also unveil giant structures, like the so-called Galactic Center X-ray gamma-ray bubbles, related to the Fermi bubbles mentioned earlier, visible as faint lobes emitting X-rays above and below the plane, evidence of energetic outflows long ago. At even higher energies, gamma-ray observations have uncovered the Milky Way's most energetic phenomena. The Fermi Gamma-Ray Space Telescope has shown us the galaxy in gamma rays, where the plane glows brightly due to cosmic rays colliding with interstellar gas, producing gamma photons, and due to exotic sources like pulsars and the aforementioned Fermi bubbles, two enormous lobes extending 50,000 light-years above and below the center, glowing in gamma rays, likely from an ancient outburst by the central region. In visible light, these bubbles are invisible, but in gamma rays, and also in X-rays and radio via related emissions, they stand out, telling us that the Milky Way's core experienced a significant energy release a few million years ago. Beyond electromagnetic waves, we have other messengers. Cosmic rays themselves, high-energy particles, constantly strike the Earth's atmosphere. Their distribution and energy spectra tell us about processes in supernova remnants and the galaxy's magnetic fields. Neutrinos, nearly massless particles that rarely interact, have been detected from a nearby supernova, 1987A in the LMC, and perhaps diffuse galactic sources, providing insight into nuclear reactions in stars and supernovae. And now gravitational waves have opened yet another window. While we haven't yet pinpointed a gravitational wave source within our galaxy, future detectors might catch waves from merging black holes or neutron stars in the Milky Way, literally allowing us to hear the vibrations of space-time from stellar cataclysms in our galaxy. All these non-visible means of observation have profoundly expanded our understanding. They let us map structures that were hidden, detect components that were unknown, and comprehend energetic processes with no optical signature. For example, before radio astronomy, we didn't know the extent of the spiral arms or the huge hydrogen envelope of the outer galaxy. Before infrared, the barred bulge was elusive, and the galactic center's star swarm was largely concealed. X-rays and gamma rays alerted us to extremely hot gas and violent events that otherwise leave little trace. Together, these techniques present a multi-wavelength portrait of the Milky Way, a galaxy humming with activity across the spectrum. In a sense, we have learned to see the Milky Way in forms of light our eyes can't perceive. Our eyes see the grandeur of the Milky Way's stars as a ghostly band, but our instruments fill in the rest of the story, revealing the cold hydrogen framework, the dusty cradles of stars, the energetic fireworks of supernovae and black holes, and the relics of past eruptions. It's like listening to a symphony, with all the instruments audible instead of just one. With each new wavelength and technique, the Milky Way's voice becomes richer and more complete, allowing us to truly appreciate the complexity and beauty of our galactic home in its entirety, not just the portion that shines in visible light. For as long as humans have existed under the night sky, the Milky Way has been a source of wonder and stories. Every culture has looked up at that pale band and interpreted it through their own lens. To our ancestors, it wasn't a collection of distant suns in a vast galaxy. It was something intimate, meaningful, often divine. The name Milky Way itself comes from ancient Greek myth. Zeus placed his infant son, Heracles, at Hera's breast while she slept, hoping the divine milk would make the baby immortal. Hera awoke and pushed the child away, and her spilled milk formed the band of light in the sky. Thus Gala, milk, became the Galacticos Kyklos, the Milky Circle. The Romans translated this to via Lactea, road of milk, which eventually gave us Milky Way. But Greeks and Romans were far from alone in their celestial imaginings. In parts of Eastern Europe and Central Asia, people saw the Milky Way as a trail of spilled grain or flour, perhaps a mythical farmer's wife or a thief dropping corn or straw along the sky. One legend speaks of a careless dairymaid spilling milk across the heavens. These pastoral metaphors tied the sky's appearance to everyday life. In one explanation, the Milky Way was called the straw thief's path. A thief stole straw, and as he fled across the sky, straw leaked from his sack, creating the pale band. Across the world, A very common theme is a celestial river. In ancient India, the Milky Way is a Kash Ganga, the Ganges river of the sky, a sacred river flowing in the heavens, mirroring the holy Ganges on earth. In traditional Chinese lore, it's the silver river, Yinhe, or heavenly river, Tianhe. One of the most famous Chinese folktales tells of this river separating two lovers, the weaver girl and the cowherd, placed on opposite sides of the sky. They became the stars Vega and Altair, with the Milky Way between them, and they're allowed to meet only once a year, on the seventh night of the seventh lunar month, when a bridge of magpies forms across the Silver River. This tale is celebrated in the Chichi festival and echoed in Japanese Tanabata, where the Milky Way is Amanogawa, the river of heaven. So to East Asian eyes, the Milky Way was a shining river that both kept lovers apart and, on rare occasions, connected them, rich with romantic and poetic meaning. Northern peoples often saw a path or road. In many Finnish, Estonian, and Siberian traditions, it was the path of birds, an observation that migrating birds seem to follow the Milky Way in their seasonal journeys. Indeed, on clear autumn nights, the hazy band could guide flocks of geese or cranes heading south. The Finnish name Linnunrata, bird's root, and similar names in Estonian and other Uralic languages reflect this. Some Native American nations also linked the Milky Way to birds. Others saw it as the path of souls. The Cherokee, for instance, envisioned it as where the dog ran, with a story of a dog carrying a cornmeal and spilling it. But the idea of a path in the sky recurs. The path of souls concept is widespread. Many indigenous peoples of the Americas saw the Milky Way as a road that spirits travel after death. To the Navajo, Diné, it was Yikais Dahi, sometimes called the Trail of the Gods or the Path of Spirits, a pathway for the deceased to reach the spirit world. The Milky Way, as a bridge between life and afterlife, also appears in ancient Egyptian ideas. Some associated it with the sky goddess Nut, arching over the earth, swallowing the sun each evening and rebirthing it by morning, with the Milky Way perhaps representing her body or a celestial Nile. In Norse mythology, some identified it as the path to Valhalla or Bifrost, the rainbow bridge's white backbone. The Milky Way's darkness and light also sparked imaginative interpretations. Many Australian Aboriginal peoples paid close attention not just to the bright starry band, but to the dark patches within it. They created dark constellations out of the absence of stars. The most famous is the Emu in the Sky, seen by several Aboriginal groups. The Coalsack Nebula, a prominent dark cloud near the Southern Cross, forms the emu's head, and the dark lane through Centaurus and Scorpius outlines its body. To them, the Milky Way's dark silhouette of an emu had cultural significance tied to the seasons and land. Meanwhile, in the Andes, the Inca also identified dark cloud constellations within the Milky Way. Animals like the llama, Yacana, traced by dark nebulae, with the llama's eyes being Alpha and Beta Centauri. These cultures looked at the Milky Way and saw not only the light of stars, but the shapes of darkness, full of meaning. In Western medieval Europe, the Milky Way was sometimes called the Road to Santiago. Pilgrims traveling to the shrine of Santiago de Compostela in Spain used the Milky Way as a heavenly guide westward, leading them toward their destination. So it gained the nickname Camino de Santiago, in the sky, or St. James's Way. This association of the Milky Way with pilgrimage and spiritual journey shows how it served not only as mythic symbol, but also as a practical navigational tool. Indeed, before modern navigation, the Milky Way was a useful nighttime compass. Its presence told direction and time of year. Its orientation changes with the seasons. To Polynesian voyagers navigating the Pacific, the Milky Way, which they saw as a great fish or canoe, was part of the complex celestial cues used to traverse vast distances. From a goddess's milk to a river of souls, from a path of birds to a guide for pilgrims, the Milky Way has meant many things to humanity. It has been woven into mythologies, used as a calendar and compass, and made a canvas for imagination. Even as science has unveiled its true nature, the cultural stories of the Milky Way remain a beautiful human response to the grandeur overhead. One can stand under a starry sky, see that misty arch, and remember that around the world and throughout time, others saw it as a heavenly river, a bridge of lovers, a road of spirits, or the milk of a divine mother. These myths and names underscore a truth. The Milky Way has always made us feel connected to something larger, whether interpreted through science or story. Even today, knowing it's a spiral galaxy full of stars, we still call it the Milky Way, a name born of ancient poetry. The scientific explanation doesn't diminish its cultural resonance. If anything, it adds another layer. We can appreciate the Milky Way as a galaxy and as the inspiration for countless tales across the world. In that sense, our galaxy is not just a physical entity, but also a tapestry of human experience and imagination, uniting past and present under the same sky. Standing here on Earth, gazing up at the Milky Way, one cannot help but feel both humbled and uplifted. Humbled, because we recognize that Earth is a tiny world orbiting an ordinary star in the outer suburbs of a vast galaxy. Uplifted, because we are a part of that vastness, born from it, connected to it, and now able to contemplate it. The realization that we live inside a galaxy among billions of others is relatively recent in human history, and it carries profound philosophical implications. It's an extension of the Copernican revolution. Not only are we not the center of the solar system or universe, we're not even central within our own galaxy. We inhabit a quiet corner of an immense cosmic city. This perspective can be deeply humbling. All of human history, every love, every conflict, every dream, and every life has unfolded on a small rocky planet orbiting one star among hundreds of billions in the Milky Way. If our entire solar system were to vanish tomorrow, the galaxy would carry on essentially unchanged. On the scale of the Milky Way, humanity is exquisitely small. Contemplating that can shrink our everyday worries and divisions in significance. National borders, political squabbles, the minutiae of our lives all fade against the backdrop of 100 billion suns. In that sense, the galactic perspective can be a unifying one. All people on Earth are in the same tiny boat, drifting together in the vast ocean of the galaxy. The Milky Way does not distinguish between nations or cultures. Its gravity holds us all alike. Recognizing this shared cosmic context might inspire a greater sense of unity, a kind of galactic citizenship of humanity. At the same time, the galactic perspective is empowering and awe-inspiring. Out of this immense galaxy, on one little world, a form of life arose that can question and understand. We humans, products of the Milky Way, can step back in our minds and reflect upon our galaxy's nature. In a poetic sense, we are the Milky Way looking at itself. As one astronomer famously put it, we are made of star stuff. The iron in our blood, the calcium in our bones, the oxygen we breathe. These atoms were forged in stars that lived and died in the Milky Way long before Earth formed. We literally carry pieces of the galaxy within us. Every one of us is a child of the stars. This knowledge can fill us with a profound sense of belonging in the cosmos. We are not outsiders looking in. We are insiders, a way for the galaxy to know itself. The Milky Way also raises one of the great questions. Are we alone in our galaxy? With hundreds of billions of stars and likely trillions of planets, it seems improbable that life, especially intelligent life, evolved only here. When you see the dense star clouds of the Milky Way, Consider that many of those stars host planetary systems. How many have planets with oceans and atmospheres? How many have beings who also wonder and look up? So far, we have no confirmation of others. The galaxy has been silent to our listening. But the sheer number of opportunities humbles any assumption that we are unique. Perhaps someday we'll detect a signal, or even find evidence of another civilization in the Milky Way, forever altering our perspective. Or perhaps life is exceedingly rare, and we are among the very few, which would make our responsibility to cherish and spread life even greater. Either possibility is mind-boggling: a galaxy teeming with life and minds, or one in which life is a precious rarity. Knowing we live in a galaxy changes how we see the night sky. For early humans, the Milky Way was a mystery to explain with myths. Now we know it for what it is, the disk of our galaxy seen from within. But that scientific understanding doesn't diminish its beauty or emotional impact. If anything, it enhances it. When we see that milky band now, we can think, those are the combined lights of uncountable distant suns, perhaps with worlds of their own. We can marvel that our eyes, simple as they are, can perceive the grand structure of our galaxy from the inside. In a way, understanding the Milky Way's true nature gives us a new cosmic mythos, not one of milk and gods, but one of stars and galaxies, of being small yet able to grasp the entirety of our home galaxy in our minds. There's a philosophical lesson in how we figured out the Milky Way's structure. Living inside it, much was hidden from us by dust and perspective. It took generations of careful observation, thought, and imagination to piece together the galaxy's form. We had to transcend our limited viewpoint, effectively take a mental journey outside the galaxy to understand it. This is a testament to human curiosity and ingenuity. It reminds us that even if we are embedded in a situation, with effort we can rise above our biases and see the bigger picture. There's a metaphor here. Often we're stuck in our own dusty problems, but by seeking a broader perspective, we can find clarity. Just as we unveiled the Milky Way's barred spiral, despite being stuck in the galactic plane. The dynamic nature of the Milky Way also offers perspective on impermanence and change. We've learned that galaxies evolve. The Milky Way is eating smaller galaxies and will eventually merge with Andromeda. Nothing in the cosmos is static, not even the seemingly eternal canopy of stars. This fosters a sense of cosmic patience. The troubles of one era, or even the lifespan of our species, are momentary flickers on the galactic timescale. While that can make our individual endeavors seem insignificant, it can also imbue us with resilience and humility. Life and consciousness, if nurtured, could adapt and continue even as cosmic conditions change. It also prompts us to appreciate the present moment. We exist at a special time when we can still see our Milky Way's spiral structure. In a distant future merged galaxy, the night sky might look very different. Right now, we have a front row seat to the Milky Way's splendor. That's a privilege of this era in cosmic history. All these insights, our smallness, our connectedness, the potential multiplicity of life, the power of perspective, the transience of cosmic forms, make the Milky Way more than just an astronomical object. It becomes a source of philosophical contemplation and spiritual wonder. Under the starry arch of the Milky Way, one can feel simultaneously insignificant and deeply significant. Insignificant because we are tiny in scale and time. Significant because we are conscious participants in this vast universe, capable of reflecting on it. It's a beautiful paradox. We are inconsequential to the galaxy, yet the galaxy is meaningful to us because we endow it with understanding and curiosity. Ultimately, living in a galaxy encourages a cosmic perspective. It invites humility, curiosity, and reverence. It reminds us we are part of a story much larger than ourselves, a story that began long before we arrived and will continue long after. But for this brief moment, the universe, through us, can reflect on itself. The Milky Way shines down, and we have learned to recognize it as our home. With that knowledge comes a profound responsibility to care for our tiny world, the precious cradle where we evolved, to seek knowledge and look outward with hope and wonder, and to treat each other kindly as co-travelers beneath the same glorious galaxy. In a universe so immense, the only way to find meaning is often to create it together. Our lives and civilizations may not shake the galaxy, but they can light up our small corner of it. Perhaps that's enough. To be conscious children of the Milky Way, striving to understand and cherish the universe that gave us life. Now, after journeying through our galaxy in mind, let us return to a single human moment under the stars. Imagine a clear, moonless night in a quiet place, far from city lights. Above you arches the luminous band of the Milky Way, shimmering white against a black sky. The air is still. You feel the earth beneath you and gaze upward. That hazy glow is no longer a mystery. You know it is the collective light of billions of distant suns, the edge-on view of our spiral galaxy from within. You recognize the dark patches as interstellar dust, and you recall that behind them are yet more stars in the very center of the Milky Way, hidden from your eyes but real nonetheless. You might even picture, in your mind's eye, the shape of the spiral arms and the halo and the embrace of dark matter extending beyond. All the structures we've discussed. Yet knowledge has not diminished the beauty of the night sky. If anything, it has enriched it. As you stand or lie there in awe, you feel the layers of meaning. You remember that every atom in your body came from this galaxy's stars. You truly are a child of the Milky Way. The band of light above is at once the river of myths and the grand reality of our island universe. The scientific facts mingle with a more primal appreciation. You feel connected to the vastness and also grounded here on your little planet. The Milky Way is no longer just a backdrop of tiny lights. It is your home galaxy, enormous yet intimate, known yet still deeply mysterious. Take a slow breath and let your eyes trace the Milky Way's arc. Perhaps you see the constellations silhouetted against it, the Summer Triangle, or Scorpius, curling toward that bright hub in Sagittarius. You see the misty star clouds densest near the center and thinner toward the edges, and you notice the dark rifts where dust veils the light of distant stars. Think of all the journeys happening beyond your sight, stars orbiting the center over millions of years, perhaps distant worlds with their own observers looking back at us. Think of how far we have come to understand this structure, and how much more there may be to learn. And then, gently, let those thoughts go. Simply feel the wonder that the ancients must have felt, the wonder of that milky river in the sky. It's the same band of light they saw. The sky links us across time. Countless generations paused here, just as you are, to admire the Milky Way. From storytellers weaving tales around campfires to astronomers at their telescopes. Now it's our turn, in this present moment, to soak in its splendor. In the stillness, you sense something transcendent. The Milky Way above, with its millions of suns, puts our lives in perspective, yet also illuminates them with meaning. We are small, but we are part of something vast and beautiful. The galaxy is immense and seemingly impersonal, yet here we are, creatures of its making, able to appreciate its light and comprehend its nature. In that sense, we give the Milky Way eyes and voice. Our eyes, our voice. As you stare upward, the boundary between out there, before we set sail among the stars, we must first sense the shape of the ship that carries us. The Milky Way, in all its splendor, is built upon an invisible architecture. Like an elaborate cathedral shrouded in fog, its grand design is partly hidden from our eyes. What holds up this starlit city? What scaffold keeps our galactic home from flying apart? To answer, we venture beyond the visible, into the domain of the unseen, a realm of gravity and ghostly matter, the invisible architecture that underpins the galaxy. Imagine a vast, dark scaffold woven from something we cannot touch or see. A web of gravity shaped by a mysterious substance known as dark matter. We call it dark, not just because it emits no light, but because it eludes direct detection, hiding in shadows beyond our instruments' reach. And yet, though invisible, it is immensely real. It sculpts the galaxy's form and governs the dance of the stars. If we could don magical glasses to see mass instead of light, we would behold a gigantic halo enveloping the Milky Way, a roughly spherical cloud stretching far beyond the galaxy's shining disk. This halo, mostly made of dark matter, is the invisible architecture, the foundation on which the visible Milky Way is built. We feel its presence through its pull. Just as a steady hand might guide dancers on a floor, the gravity of dark matter guides the stars in their orbits. In the outskirts of the galaxy, far from the brilliant core and spiral arms, stars and clouds of gas whirl around the center at astonishing speeds. Logic suggests they should drift away into the depths of space. There simply isn't enough visible mass in stars or gas to hold them. Yet, they remain bound, as if tethered by phantom strings. These tethers are the gravitational grip of dark matter, an unseen mass whose influence permeates the galaxy. It forms an invisible halo, extending hundreds of thousands of light years beyond the edge of the visible Milky Way, cocooning it like an unseen guardian. This hidden architecture doesn't glow or sparkle, but it makes itself known in other ways. Picture the galaxy like a vast, spinning carousel. In a normal carousel, things at the edge move more slowly than those near the center. But in our galaxy, stars in the far suburbs orbit at nearly the same speed as those closer in. It's as if the carousel's rim has extra hidden weight, providing the needed gravity to keep those outer stars from escaping. That extra weight is dark matter. It is the silent partner to all the shining stars, outweighing them many times over. For every star we see twinkling in the Milky Way, there is far more mass hiding in the dark, perhaps 5 to 10 times more. This dark mass forms the scaffold, the architecture without which the beautiful glowing disk of our galaxy would not exist as we know it. But dark matter is not the only component of the invisible architecture. Gravity itself is the architect, the master planner that molds matter into structure. Long ago, before the Milky Way even had its name or shape, gravity drew together a diffuse cloud of matter. It began to pull everything inward, spinning and flattening the gathering material. Like an artist shaping clay, gravity sculpted the first outlines of our galaxy. It made the wispy tendrils of primordial gas collapse into denser clumps, igniting the first stars. Over billions of years, it orchestrated mergers of smaller protogalaxies, each merger guided by the gravitational hand of dark matter, halos merging as well. The Milky Way grew within a gravitational cradle, an underlying framework stretching through space like the skeleton of a great beast. Even today, gravity's influence extends beyond the stars. The space between galaxies is not entirely empty. It is threaded by filaments of dark matter, forming a cosmic web. Our Milky Way lives at the intersection of these filaments, like a pearl caught in a spider's web of invisible threads. Through these threads, clumps of matter, both dark and ordinary, flow inward. One might imagine cosmic tides, slow and inexorable, delivering fresh gas and even small galaxies toward the Milky Way. This ongoing infall continues to shape our galaxy, guided by the unseen architecture of the cosmic web. We drift in a gentle current of gravity, a river whose banks are made of dark matter. Close your eyes and picture the Milky Way not just as stars, but as an enormous gravitational presence. Feel the invisible arms that extend far beyond the furthest star, reaching out into intergalactic night. This is the scaffold that holds us, the container of our existence on a galactic scale. Stars, nebulae, planets, and people all live embedded in this gravitational field, moving along paths choreographed by an architecture we perceive only indirectly. The invisible architecture humbles us. It reminds us that what is most important is often hidden. We live in the luminous beauty of a spiral galaxy, but that beauty is underwritten by something dark, massive, and enigmatic. The stars trust this structure. They orbit faithfully, generation after generation, as if following ancient roads built by an unknown engineer. We too are sustained by this invisible framework. Without it, our sun might wander off into the void, carrying Earth and us with it into solitude. Instead, we remain part of this grand rotating city of stars, anchored by a dark, unseen sea of gravity. As our journey continues, keep this concept close to your heart. Not everything that matters can be seen. The Milky Way's brilliance rests upon an invisible foundation. In life and in galaxies, the unseen often guides the seen. We move onward now into the visible realm of the Milky Way, but we do so knowing that an invisible architecture holds it all together, like the silent knowledge beneath spoken words, or the unseen wind shaping the dunes. In this galaxy, as in ourselves, there is more than meets the eye. Anatomy of the Milky Way. Now that we sense the hidden scaffolding, let us step back and behold the anatomy of the Milky Way, the grand design of our galactic home. If we could rise above the disk and look down from far away, what would we see? We would witness a spiral galaxy in its prime, a flat disk of stars and gas, with graceful arms winding outward from a bright central region. It would resemble a vast rotating pinwheel strewn with glittering lights. This is the city of stars we call home, a cosmic metropolis containing everything we know. At the center of it all lies the galactic bulge, a rounded hub of stars that swells above and below the flat plane of the disk. The bulge is like the city center, crowded, bustling, and ancient. Its stars are mostly old amber-colored beings, many billions of years in age. Some of these stars are almost as old as the universe itself, born when the galaxy was young and the cosmos had barely emerged from darkness. The bulge is roughly spherical or slightly elongated. In fact, observations show that the Milky Way has a central bar, a long horizontal concentration of stars crossing the core. Think of it as a glowing bar of stars at the galaxy's heart, with the bulge wrapped around it. This stellar bar acts like a cosmic traffic system, channeling gas inwards and helping to form new stars and feed the central region. The bulge and bar together form the beating heart of the Milky Way, densely packed with stars dancing in complex orbits. Extending outward from the bulge are the spiral arms, the most striking feature of a spiral galaxy. The Milky Way sports multiple spiral arms, curving out like swirls in a whirlpool. Each arm is a region of higher density. Imagine waves in the galactic disk, where stars and gas get slightly bunched together as they orbit the center. In these denser waves, gas clouds compress and new stars ignite, lighting up the arms with hot, young suns that shine blue-white. Nebulae, great clouds of glowing gas, pepper the arms, marking the nurseries where stars are born. From above, the arms would appear like starlit ribbons or the tendrils of a vast cosmic jellyfish rotating slowly around the core. They have poetic names derived from constellations we see in their directions: Perseus Arm, Sagittarius Arm, Scutum Centaurus Arm, Carina Arm, and the smaller Orion Spur where our Sun resides. Our solar system is currently nestled in this Orion Spur, a minor arm or branch between major arms, about 27,000 light-years from the galactic center, halfway out in the disk. We truly live in the galactic suburbs, a quiet neighborhood between busier spiral arms. The disk itself, which contains the spiral arms, is a marvel. A broad, thin plane of stars, gas and dust, roughly 100,000 light-years across in diameter. To give a sense of scale, that is about 1e5 light-years from one end to the other. In miles, a number so large, about 600 trillion, that it defies comprehension. Yet, despite its vast width, the disk is relatively thin. only about 1,000 light-years thick in the main stellar layer. In proportion, it's much thinner than a pancake. The Milky Way is a truly flat system. If the galaxy were reduced to the size of an old vinyl record, the disk would be like a razor-thin film, and the bulge a small bump at the center. Within this disk, stars orbit the center in nearly circular paths, like billions of bees swarming around a hive. They move in orderly fashion, although each carries its own slight up and down motion, giving the disk some thickness. There are actually two components to the disk: a thin disk containing most of the young stars, gas and dust, where spiral arms are prominent, and a thick disk of older stars that extends a bit further above and below the plane. The thick disk's stars are fewer and older, hinting at a past era of the galaxy when star formation and dynamics were a bit different. Together, these disks form the galactic equivalent of the streets and districts where our tale of star life unfolds. Encircling everything is the stellar halo, a spherical distribution of stars and ancient clusters that envelop the disk and bulge. The halo is sparse. Its stars are like lone wanderers, often old and feeble in light, scattered in a vast volume. Among them are the globular clusters, about 150 tight balls of very old stars orbiting the galactic center in extended, inclined paths. These clusters are fossils of an earlier time, some formed in the Milky Way's youth, others perhaps the remnants of small galaxies consumed by the Milky Way long ago. The stellar halo reaches far beyond the disk, fading into the dark. It's the galactic countryside, mostly empty, but for those isolated stars and clusters. As we learned in the invisible architecture, this stellar halo is just the visible tip of a much larger dark matter halo that extends even farther and holds the whole system in its gravitational grip. Imagine for a moment we could view a cross-section of the Milky Way, a side view. We'd see the bulge in the middle, a central swelling of stars. Stretching out from it is the thin disk, narrow and bright, with spiral arms embedded within. Slightly puffed up around the thin disk is the thick disk, a dimmer and broader spread of stars. Surrounding everything is the faint halo of ancient stars and globular clusters. This is the layered anatomy of our galaxy, a structure as intricate as any organism. Each part, bulge, bar, thin disk, thick disk, arms, halo, has its own character and story, yet all are bound together by gravity into one rotating system. Within this grand design, our Sun is a tiny speck. It takes about 250 million years for the Sun to complete one orbit around the galactic center, a galactic year. The last time we were at our current position in orbit, there were dinosaurs just beginning to roam Earth, and the first flowers were blooming. In that time, the Sun has journeyed around the galaxy perhaps 18 to 20 times in its 4.6 billion year life. This illustrates both the immense scale of the Milky Way and the surprisingly dynamic nature of our position in it. We are moving along with the entire solar system at roughly 230 kilometers per second, over 500,000 miles per hour, just to keep up with the galactic rotation, like riders on a massive carousel. The Milky Way's anatomy is not rigid. It's a living structure. The spiral arms rotate around the center, though not like solid blades. Stars drift in and out of them. The bar in the center slowly twists. The very disk can ripple. Interactions with satellite galaxies can send waves through it, causing subtle warps. In fact, observations show our disk is slightly warped, like a stretched-out ripple, likely due to gravitational interactions with neighbors or remnants of old mergers. So one might picture the Milky Way not as a static pinwheel, but as a swaying spiral, its disk breathing and waving over long timescales, its arms a pattern in motion. To truly appreciate this anatomy, consider the unity of it. Hundreds of billions of stars, each with its own orbit, many with their own planets, together forming these coherent structural components. From our vantage point on Earth, inside the disk, we see the Milky Way as that misty band across the sky. That band is essentially our edge-on view through the disk, a cross-section of countless distant stars concentrated along the plane. The dark patches we see, like the Great Rift dividing the bright Milky Way in the summer sky, are not empty of stars, but choked with dust that blocks starlight. Those are part of the disk's anatomy too, dark nebulae that silhouette against the starry backdrop. It is humbling to realize that for a long time, we didn't even know the true shape of our galaxy. Early astronomers peering with small telescopes, or just eye, only saw that band and tried to guess our imagely in the 20th century. Did we map the Milky Way's spiral structure, using telescopes sensitive to radio waves and infrared light, which can penetrate dust, and by cataloging the distances of stars and clusters. Today, missions like Gaia have measured precise positions and motions of over 1 billion stars, allowing us to cartograph the Milky Way's structure with unprecedented accuracy. Yet, being inside it, we still find pieces of the puzzle gradually, like a person mapping a forest from within, tree by tree. In summary, the Milky Way's anatomy can be thought of in layers and components. A luminous central bulge with a bar, a sprawling disk with spiral arms, thin disk plus a thicker disk of older stars, and a vast halo beyond. It is a majestic aggregation of matter and stars, structured yet fluid in form. Think of the Milky Way as a great cosmic tree. The bulge is the sturdy trunk. The disk and arms are the wide branches and leaves catching the light, and the halo is the sparse canopy spreading out into the sky. Or imagine it as an island. The bulge is a mountainous continent at the center. The disk is the flat expanse of land and sea around it with spiral currents, and the halo is the thin atmosphere and lonely outlying islets. This is our galaxy's body, magnificent and humbling. Knowing its anatomy, we are ready to delve deeper into its organs and processes. We have seen the map. Now we turn to the citizens of this galaxy, the stars themselves, and how they live and evolve in this stellar city. Stellar population and evolution. Every point of light in the Milky Way is a story in itself. A star shining with nuclear fire, perhaps orbited by planets, perhaps destined to explode or fade. In the Milky Way's vast population, there are stars of all ages and sizes, from brilliant blue giants to faint red dwarfs. Stellar population and evolution is the study of these billions of lives. How stars are born, how they age, and how they die, all within the galactic community. As we traverse this topic, imagine walking through a cosmic garden where stars are like flowers at different stages, buds, blooms, withering stalks, all contributing to the cycle of life in the galaxy. Astronomers classify stars in our galaxy broadly into populations. The population 1 stars are those like our Sun, relatively younger in cosmic terms, and richer in heavy elements, elements heavier than helium, because they are born from recycled materials. They tend to reside in the disk, especially the spiral arms, where active star formation is ongoing. Then there are population 2 stars, old, metal-poor stars, fossils from the early galaxy. These often inhabit the bulge and the halo, like in globular clusters or as solitary halo stars. There is even a theoretical population 3, the very first stars born in the universe, extremely metal-poor and long gone now, but their imprint might survive in some of the oldest Pop 2 stars. In the Milky Way, stellar evolution is not just theory, it's on full display. Consider the spiral arms. They are studded with stellar nurseries where new stars take shape. Giant cold clouds of molecular gas and dust, colossal wombs known as molecular clouds, collapse under gravity in pockets, forming clusters of newborn stars. Within these nebulae, we find young protostars still accreting mass, often hidden in dust, and bright newborn stars whose intense radiation causes the surrounding gas to glow. The Orion Nebula, for example, in our Orion Spur, is a nearby region where such processes occur, and the Carina Nebula is another dramatic stellar nursery, featuring massive stars that formed just a few million years ago. These newborn stars are typically hot and massive, shining blue-white and living short, brilliant lives. They are often found in loose groups or clusters, like cosmic kindergartens of stars. The presence of such O and B-type stars in the spiral arms is what makes the arms stand out with a bluish tinge. These stars are luminous beacons, but they burn out quickly in a few tens of millions of years, and thus never stray far from their birthplaces. As stars age, they drift away from such nurseries and join the general population of the galactic disk. Intermediate mass stars like our Sun live for billions of years, orbiting peacefully, slowly using up their hydrogen fuel. They may drift around the galaxy many times. Our Sun, for instance, has gone around the center about 20 times and witnessed the changing arrangement of spiral arms and clouds around it. Over time, stars like the Sun will exhaust their core hydrogen and expand into red giants, glowing with a cooler, reddish hue, but enormously larger and more luminous than before. In this phase, they puff off their outer layers, enriching the surrounding space with elements formed in their interiors. Many such aging stars can be found in the Milky Way. Look toward the bulge, and you find myriad red giants crowding the region, evidence of older stellar generations. Some stars live violent, short lives. The high-mass stars, perhaps born in those same clusters, race through their nuclear fuel in mere millions of years. They swell into supergiants, some red, some blue, depending on mass and stage. In the Milky Way, famous examples include Betelgeuse, a red supergiant in Orion, nearing the end of its life, and Rigel, a blue supergiant. When their cores can no longer sustain fusion, these massive stars die in titanic explosions, supernova, blasting their guts of heavy elements into space. Each supernova is like a brief, tragic fireworks show, outshining whole star clusters for weeks. Our galaxy has witnessed countless such explosions over its lifespan. They are part of its ecosystem. The remnants of these explosions, expanding clouds of gas like the Crab Nebula or Veil Nebula, lace the galaxy, adding to the diffuse background of matter that will one day form new stars. And what remains of the star itself can be a neutron star or a black hole, ultra-dense cinders of stellar cores that often quietly linger in the galaxy's disk or halo. Meanwhile, low-mass stars, far more common, especially faint red dwarfs that make up perhaps the majority of stars by number, live incredibly long, slow lives, longer than the current age of the universe in many cases. These red dwarfs form in the disk as well, and will burn their fuel so gradually they might outlast the galaxy's current form. These unobtrusive stars form the quiet backbone of the Milky Way's stellar population, too dim individually to notice, but collectively contributing significant mass. Stellar evolution in the Milky Way is a cycle. New stars form from gas enriched by older stars, live their lives, and then return material to the galaxy when they die. This cycle gradually changes the content of the galaxy. Early generations had almost no elements like carbon, oxygen, iron. Those were forged in stars and supernovae. Later generations, like the Sun, were born from clouds already seeded with these elements. Thus, our Sun contains about 2% of its mass in elements heavier than helium. Small, but enough to allow the formation of rocky planets like Earth. Without countless star lives and deaths before it, the Sun would have had no planets, or at least no solid ones, and we would not exist. The Milky Way's star population is thus intimately linked to everything around us, including life. The galaxy also sorts its stars by location. In the halo, we find primarily those old population 2 stars, with very low metallicity, a sign they formed when heavy elements were scarce. Many might be remnants of smaller galaxies the Milky Way gobbled up long ago. We'll get to that in galactic cannibalism. These halo stars often have orbits that plunge in and out of the disk at steep angles or swing far out, not the orderly carousel orbits of the disk stars. In the bulge, Stars are again old on average, but slightly more enriched than the halo, and their orbits are randomly oriented, creating a spherical distribution. Some bulge stars may have formed in early mergers or in early starbursts in the young Milky Way. In the thin disk, we have stars spanning a range of ages, from newborns just a few million years old in spiral arms, to intermediate 5-billion-year-old stars like the Sun, to older disk stars maybe 8 to 10 billion years old. The thin disk tends to host stars with higher metallicities, meaning each generation has incorporated more of those heavy elements. The thick disk stars are older, maybe 10 to 12 billion years, and have lower heavy element content. They might be the remnants of the early disk formed shortly after the halo, possibly created or heated during an ancient merger event that puffed up the disk. The Milky Way is essentially a stellar family tree. At its base are the ancient ones, the halo stars and globular clusters that can be over 12 billion years old, tracing back to the galaxy's youth. Then come the thick disk stars, slightly younger. Then the majority of the thin disk stars like our Sun, younger still. And at the tips of the branches, constantly budding, are the new stars being born today. The galaxy's current star formation rate is a few solar masses per year, meaning on average, a few new stars, some massive, many small, spark into existence each year across the entire galaxy. In regions like the Carina Nebula or the Sagittarius Arm, one can witness these newborns emerging and lighting up their surroundings. Interestingly, there's a chemistry to this evolution. The Milky Way's stars have gradually changed the composition of the galaxy's gas. Early supernovae seeded space with iron and magnesium. Dying red giants puffed out carbon and nitrogen. Neutron-star collisions, rare but dramatic, may have forged gold and platinum and flung them into space. Over billions of years, the galaxy's gas has become a richer chemical stew, enabling new types of objects, like planetary systems with solid planets. Astronomers sometimes call this process chemical evolution, and they track it by measuring the spectra of stars, reading the barcode of elements present. In doing so, they can identify stars that share a common origin or era. For example, one might find a group of stars spread through the halo that all have a particular scarcity of iron but excess oxygen, clues that they might have come from the same long-gone dwarf galaxy that had its own unique chemical history. Stellar evolution also drives cosmic timekeeping. The color and brightness of stars across the galaxy tell us the epochs of formation. The presence of massive blue stars indicates ongoing or recent star formation, since those don't live long. The presence of many red giants indicates an older population. In the Milky Way, we see both. The arms are lit with blue stars, the bulge with red giants. We are living in a galaxy that is still actively forming stars, though not as furiously as it once did in its youth. Perhaps our Milky Way in its past had starburst periods when it churned out stars at a much higher rate, maybe triggered by mergers. Now it's in a more quiescent middle age, creating stars steadily but more slowly. However, middle age does not mean inactivity. Right now, as you listen, somewhere in the Milky Way, a star is exploding in a supernova, ending its life. Somewhere else, a cool cloud is fragmenting, and the spark of a new star is catching fire. A sun-like star might be quietly swelling into a red giant and engulfing any close planets. A binary pair of stars might be exchanging mass in a delicate gravitational dance, one siphoning from the other, perhaps to eventually trigger a nova eruption. The galaxy is alive with stellar happenings at every moment, a grand fireworks show in extreme slow motion. Each star also carries within it the memory of the galaxy's evolution. By studying them, scientists piece together how the Milky Way grew. For instance, they found some stars in the halo moving backward relative to the general rotation, evidence of an ancient collision that brought in stars on different orbits. They found that the thick disk has distinct chemistry, suggesting a turbulent formation, possibly a massive merger about 10 billion years ago that heated the early thin disk. Thus, the stellar populations and their properties are like pages in a history book. We live among these stars, unaware in daily life of their grand narratives. But if you step back, you can see that the Milky Way's stellar population is a complex tapestry, with threads of different ages and origins woven together by gravity. Ultimately, stellar evolution in the Milky Way is a story of continuity and renewal. Stars are born from the ashes of their ancestors and return material to keep the cycle going. It's poignant to think that in the future, long after we're gone, the atoms that currently make up Earth and our bodies might one day be blown into space by the sun's distant red giant phase, becoming part of a nebula, perhaps to be incorporated into new stars or planets. We are a part of this cosmic recycling. Our galaxy is not a static collection of eternal lights. It is a dynamic, evolving ecosystem of stars. As we leave the stellar garden, marvel at its variety, the hot, young stars shining like blue-white fireworks, the stately middle-aged stars like our sun nurturing planets, the elderly red stars casting a gentle glow, the ghosts of stars, white dwarfs, neutron stars, black holes, remnants that whisper of lives that came before. The Milky Way contains all of these in vast numbers. It's a stellar society spanning all stages of existence. With an appreciation for the lives of stars, we proceed to consider the material that both creates and is created by those stars, the gas and dust that fill the spaces between stars, the substance from which new worlds emerge and into which old ones dissolve. Gas and dust. Between the stars of the Milky Way lies the interstellar medium, a diffuse mixture of gas and dust that is the bloodstream of the galaxy. Though the night sky might look like mostly empty space with isolated stars, in truth, the galaxy is filled with this very thin matter. Gas and dust weave silently through the Milky Way's disk, concentrating in some places and dispersing in others, fueling starbirth and absorbing starlight. This is the galactic ecology's raw material, the substance that makes new stars and planets possible. It is also the main obstacle to our view, painting dark brushstrokes across the glowing canvas of the Milky Way when seen in visible light. What is this gas? Mostly hydrogen, the simplest and most abundant element, with a seasoning of helium and traces of heavier elements. In some regions, it's hot and ionized, in others cool and molecular, spread thinly on average, just a few atoms per cubic centimeter in typical regions, far emptier than any vacuum we can create on Earth. It nonetheless adds up across the vast reaches of space. Gas constitutes a significant fraction of the galaxy's normal matter. If you could gather all the gas in the Milky Way, it would equal billions of suns in mass. And the dust? Tiny solid grains, submicroscopic, composed of elements like carbon, silicon, oxygen, iron, the ash of stars, forged in supernovae, or the winds of red giants. Each dust mote is perhaps like a fine soot or sand grain, often coated with ices or organic molecules in cold clouds. Dust might only make up 1% of the mass of the interstellar medium, but its impact is outsized. It is extremely effective at blocking and scattering light. It's the dust that creates those prominent dark rifts that cleave the Milky Way's band in the sky, giant dust clouds obscuring the stars behind them. To our eyes, those regions look like cosmic voids, but truly, they are filled with material, just not luminous in visible light. In fact, those dark clouds often harbor the conditions for future star formation, hiding embryonic stars in their lightless embrace. Gas and dust often gather together. In the spiral arms, as density waves pass through, gas clouds get compressed. Picture vast clouds, tens of light years across, cold and quiet, primarily molecular hydrogen, with dust sprinkled in. These are the giant molecular clouds, the cradles of stars. One such cloud in the constellation Orion is visible to us as a faint, hazy patch, the Orion Nebula, where young stars are lighting up the gas. Other clouds are entirely dark, detectable only by the way they block background starlight or via radio emissions from molecules inside them, like carbon monoxide, which astronomers use as a tracer. These clouds can contain the mass of thousands or even hundreds of thousands of suns. Within them, dust shields the interior from harsh starlight, allowing molecules to form and temperatures to drop to just a few tens of degrees above absolute zero. In these frigid, dense pockets, gravity can overcome pressure and cause parts of the cloud to collapse, initiating star formation. Thus, gas and dust are the maternity wards of the galaxy. As new stars ignite inside a cloud, their radiation and stellar winds begin to disperse and sculpt the gas. They create glowing H2 regions, zones of ionized hydrogen that shine with a reddish-pink hue in photographs. These nebulae are essentially the cloud's announcement that stars have been born. The Trifid Nebula, the Lagoon Nebula, the Eagle Nebula, with its famous pillars of creation. These are all examples within our Milky Way of gas, lit up by newborn star clusters, captured in stunning detail by our telescopes. In these images, we often see towers and pillars of denser gas resisting the onslaught of radiation, sometimes harboring yet more protostars at their tips. The interplay of starlight and cloud creates beautiful structures, like cosmic sculpture parks carved by ultraviolet light. Eventually, the young star's energy blows away the remnants of the parent cloud, dispersing the gas and dust back into the general interstellar medium. There, the material may drift until another spiral arm or compression gathers it again. Not all gas is in cold clouds. There is also warm interstellar gas spread throughout the disk, partially ionized by ultraviolet starlight, creating a very tenuous plasma that fills much of the volume. There are hot bubbles too, cavities blown by supernova explosions where gas has been shock heated to millions of degrees and is expanding outward. The galaxy's disk likely has a patchwork of these phases: cold, dense clouds, warm, diffuse gas, and hot ionized bubbles. They coexist like different climates across the lands of the Milky Way. Gas and dust serve as a record of events. When we find certain heavy elements or isotopes in the gas, we know a supernova contributed them. When we detect complex organic molecules in a cold cloud, we realize chemistry is happening in space. Molecules like formaldehyde, alcohols, even simple sugars and amino acid precursors have been identified in interstellar clouds. It's astonishing. In the emptiness of space, tiny dust grains can catalyze the formation of complex molecules so that clouds many light years away hold some of the same chemical ingredients that on Earth lead to life. This interstellar chemistry is a rich field. One could say the galaxy has its own chemistry lab, continuously running experiments in the cold and dark, forging new molecules that one day might be incorporated into planets or even life forms. We owe a lot to dust. It facilitated the cooling of clouds to form stars, and later, in protoplanetary disks around new stars, dust grains clumped to form planetesimals and eventually planets. But dust also obscured our view. For centuries, it hid the true extent of the Milky Way. Early star counters like William Herschel in the 18th century tried to gauge the galaxy's size by counting stars in different directions, not realizing that dense dust clouds blocked the light in some directions. This led to an underestimated size and a mistaken idea that the sun might be near the center of the galaxy. Only later did astronomers like Harlow Shapley realize, by studying globular clusters, which lie outside the dust of the disk, that the center of the Milky Way was far away in Sagittarius, and that our galaxy was much larger than previously thought. The dust had fooled us by dimming distant stars. Today, we have overcome dust's veil by observing at different wavelengths. Infrared light can penetrate dust much more effectively, allowing telescopes like Spitzer and now the James Webb Space Telescope to peer into dusty regions and see stars being born. Radio waves from certain atoms or molecules, like the 21 centimeter line of neutral hydrogen or rotational lines of CO, allow us to map the gas distribution throughout the galaxy, dust or no dust. These techniques revealed the spiral arm structure by tracing the gas that makes them up, even when those arms lie on the far side of the galaxy, hidden behind intervening dust. In fact, one of the first maps of the Milky Way's spiral structure came from radio observations of hydrogen gas. The dust, which once hid our galaxy's structure like a veil, has had that veil lifted by modern astronomy. Gas also connects the Milky Way to its environment. The outer reaches of the galaxy's halo contain very diffuse gas clouds, some of which are left over from interactions with satellite galaxies. A famous example is the Magellanic Stream, a long ribbon of gas trailing behind the large and small Magellanic Clouds, two of our satellite galaxies, as they orbit the Milky Way. This stream, tens of degrees across the sky, is essentially those galaxies' gas being stripped and drawn toward our own. Eventually, that gas may rain down onto the Milky Way's disk, galactic rain, and fuel future star formation. There are also high-velocity clouds, mysterious giant blobs of gas moving quickly relative to the rest of the galaxy, possibly remnants of past encounters, or cold gas from intergalactic space captured by our halo's gravity. Within the disk, gas moves and flows. As the galaxy rotates, differential rotation can shear giant clouds, draw them into spiral patterns. When supernovae explode, they can send out shockwaves that compress nearby gas, potentially triggering new star formation in surrounding clouds, a process akin to a chain reaction of starbirth. Alternatively, multiple supernovae can combine their shock power to punch holes in the disk and blow gas out into the halo, creating galactic fountains of hot gas that eventually cool and fall back. In this way, gas cycles not just in and out of stars, but also between disk and halo in a circulation often called the Galactic Fountain. The dust, for its part, sometimes shows us beautiful phenomena. In the densest clouds, dust is so opaque that optical light can't get through. But if there are bright stars nearby, dust can reflect their light, creating reflection nebula. Ethereal blue glows near young stars. Blue because dust scatters blue light more easily, similar to why our daytime sky is blue. We see this in the Pleiades star cluster. The hot young stars are surrounded by a blue sheen from dust reflecting their light. Dust also causes distant stars to redden. Since blue light is scattered out, more red makes it through, a clue to its presence. As we float conceptually through a spiral arm, we would pass through regions of dense gas and dust where stars are forming, then into clearer spaces where older stars roam, and perhaps past the bubbles of prior supernova. It would be like driving alternately through foggy patches and clear skies on a country road at night, sometimes seeing only nearby things, other times seeing far. In a poetic sense, gas and dust are the breath of the galaxy. They move, they flow, they condense and dissipate as the Milky Way lives and evolves. They are invisible to our unaided eyes, yet they make their presence known through the twinkle of starlight. Stars twinkle partly due to Earth's atmosphere, but interstellar gas can also cause scintillation or dimming over vast distances, and through the absorption of light, carving dark river-like shapes in the Milky Way's band in the sky that inspired so many myths. One such dark shape, visible from Earth's southern hemisphere, is the Coal Sack Nebula, a prominent dark cloud in the Crux constellation, which appears as a big hole in the Milky Way's starband. Australian Aboriginal peoples saw such dark clouds as significant shapes as well. Some saw an emu outlined in the darkness against the Milky Way. These cultural interpretations were early acknowledgements of interstellar dust's visual effect, long before science understood them as clouds of dust. Consider also that the interstellar medium whispers with electromagnetic radiation. The 21 centimeter radio whisper of neutral hydrogen permeates the galaxy. If you tune a radio telescope to that frequency, you can literally detect the diffuse hydrogen gas between the stars. It's a very faint signal, but it's everywhere, a kind of secret language that atoms are speaking across the galaxy. Using it, astronomers map spiral arms and measure rotation. As we appreciate gas and dust, we should also note the role of galactic magnetic fields. Though hard to imagine, our Milky Way has a magnetic field threading through its gas, a bit like the Earth has a field, though far weaker, on the order of microgauss. These magnetic lines influence the motion of charged particles and the alignment of dust grains. Sometimes we can detect the polarization of starlight caused by dust grains aligning with magnetic fields, giving us a glimpse of this invisible component. It's as if the galaxy has an unseen lattice that can gently steer particles, another layer of complexity in the interstellar medium. These fields might help channel cosmic rays, high-speed charged particles, through the galaxy and possibly affect star formation by providing pressure in gas clouds. In sum, gas and dust are the Milky Way's substance of creation and change. They form the clouds that birth stars, carry the products of stellar death, obscure and redden the light, and bridge the space between stars with a tenuous presence. They are, in a way, the memory of the galaxy's past and the womb of its future. Every star that will ever shine in the Milky Way will come from the gas and dust that float among the current stars. And every star that dies will return much of its substance to that reservoir. It's a cycle of cosmic reincarnation. Now, having explored the diffuse media that bind the stars, let us journey to the center of the Milky Way, a place both wondrous and forbidding, where the density of stars soars and an enigmatic darkness sits enthroned at the core. The galactic center. Toward the constellation of Sagittarius, hidden behind swathes of dust, lies the Milky Way's mysterious capital, the galactic center. This is the central hub of our galaxy, a place of extremes and secrets. If the Milky Way is a city of stars, then the galactic center is downtown, vibrant, crowded, and always bustling, yet also home to the darkest, most enigmatic figure in our galaxy's story, a supermassive black hole. Approaching the galactic center, in our mind's eye, since physically it's 26,000 light-years away, the first thing we'd notice is the sheer density of stars increasing. In the inner few hundred light-years, stars are packed like a glittering swarm. Within just 1 light-year of the center, it's estimated there are millions of stars. Compare that to our neighborhood around the sun, where the nearest star is over 4 light-years away. In the galactic center, stars can be only weeks of light travel apart from each other. The night sky from a planet in that region would be dazzling beyond imagination. Darkness scarcely exists, as you'd be surrounded by countless brilliant stars in every direction. Most of these central stars are older, redder stars, members of the bulge population. But intriguingly, intermingled among them are some blue stars, surprisingly young stars found very close to the black hole. How they got there is an active question in research. Possibly they formed from gas, funneled to the center, or maybe they were brought in as part of star clusters that migrated inward. Regardless, it means the galactic center is not just a graveyard of old stars. New life can spark, even in this hectic environment. Now, at the very core, at the precise center of the Milky Way's rotation, resides Sagittarius A, pronounced Sagittarius A star, the supermassive black hole of about 4 million times the mass of our Sun. It's currently quiet, a sleeping giant, but it profoundly affects its neighborhood. Stars closest to it are whipping around at speeds up to a few % of the speed of light, caught in its intense gravitational grip. We know this because astronomers have observed these stars, the so-called S-stars, over decades, tracking their orbits using infrared telescopes that can see through the dust. One star, named S2, orbits the black hole on a highly elliptical path that takes it within just 17 light-hours of the black hole, about 120 AU, only a few times farther than Neptune is from our Sun, at its closest. At that point, S2's speed is an astonishing 3% of light speed, 5,000 km/h. It completes one orbit every 16 years. Watching these stars swing around an unseen point showed conclusively that an extremely massive, compact object, a black hole, must lie at the center. This earned scientists like Andrea Ghez and Reinhard Genzel Nobel Prizes, as it provided some of the best evidence for the existence of supermassive black holes. Standing near the black hole, though one cannot truly stand there, one would witness bizarre effects. The gravitational field is so strong that light from stars behind it gets bent and distorted. Time itself runs a bit slower, closer to the black hole compared to farther away, a result of general relativity. Yet, Sagittarius A is relatively gentle as far as black holes go, because it's in a quiet phase, not actively devouring large amounts of matter right now. If it were active, we would see a bright beacon of high-energy radiation, X-rays, etc., and perhaps jets of particles shooting out from the poles, as seen in quasars. Instead, our black hole dines modestly. Occasional small gas clouds or asteroids might wander too close and get swallowed, producing flares. Indeed, astronomers have seen occasional X-ray and infrared flares from Sagittarius A, likely from small chunks of matter heating up just before disappearing across the event horizon, the point of no return of the black hole. The environment around the black hole is not empty. There's a swirling disk of gas and dust, though currently thin, known as an accretion flow. There are also clumps of matter like the intriguing object called G2, initially thought to be a gas cloud on a collision course with the black hole in 2014, but which survived the encounter and might conceal a star at its core. Additionally, the central region houses some unique astrophysical objects. Clusters of massive stars, the Arches and Quintuplet clusters, perhaps formed in starbursts a few million years ago, and many pulsars and X-ray binaries likely exist there, though they are hard to detect due to crowding and interstellar absorption. Moving out a bit, say within the inner few hundred light-years, what we call the central molecular zone, the gas density increases. There are massive molecular clouds swirling around the center, some arranged in a ring or torus about 2 to 5 light-years from the black hole, often called the circumnuclear disk. These clouds are subject to strong tidal forces and sometimes fall inward, feeding the black hole in dribs and drabs. The region also has unusually strong magnetic fields and cosmic ray activity. It's as if the vicinity of the galactic center is a different world compared to the quieter suburbs where we live. One of the most remarkable large-scale features tied to the galactic center are the Fermi bubbles. In 2010, scientists using the Fermi Gamma Ray Space Telescope discovered 2 enormous lobes of high-energy emission extending above and below the plane of the galaxy, centered on the core. Each bubble is about 25,000 light-years tall. They rise like twin balloons or mushroom clouds from either side of the nucleus. These bubbles shine in gamma rays and X-rays, indicating they are filled with extremely hot gas and cosmic ray particles. They likely attest to an energetic event in the Milky Way's center a few million years ago, perhaps a period when Sagittarius A devoured a batch of matter and blew out a pair of jets, or a burst of star formation and supernovae in the core that drove a galactic wind. Today, the bubbles are fading, but still glowing, ghostly echoes of that past activity. If we had gamma-ray vision, the sky would have 2 huge ovoid shapes north and south, dwarfing the full moon. These show that while the galactic center is relatively calm now, it hasn't always been so. It has had its quasar-like moments, or burps. From a human standpoint, if you could travel to the galactic center, ignoring lethal radiation and such, the sight would be awe-inspiring. Stars everywhere, a gentle reddish hue from myriad red giants, intense orbital dynamics, and at the very heart, a featureless dark void marking the black hole, perhaps detectable not by sight, but by the motion of stars and by a faint glow of doomed matter around it. Actually, in 2022, the Event Horizon Telescope collaboration gave us our first image of Sagittarius A, a ring of radio emission around a dark center, the black hole's shadow, a bit like the famous photo of the M87 galaxy's black hole, but much smaller in angular size. It confirmed the presence of the expected event horizon silhouette, further proof of the behemoth lurking there. Culturally and historically, the galactic center was unknown to us until radio astronomy. In visible light, that direction is obscured by thick dust clouds, like the Great Rift. We only realized something special lay there when in the 1950s, strong radio emissions, Sagittarius A region, were detected. Over time, multi-wavelength observations peeled away the layers of obscuration. Now we know Sagittarius A not as just a radio source, but as a black hole. If Earth's night sky were not obscured by dust towards Sagittarius, who knows? Perhaps ancient astronomers would have built temples or stories around a bright object there. But instead, it was hidden, maintaining its mystery until modern times. The galactic center is also rich in molecules. The clouds in this zone have produced some of the most complex molecules detected in space, likely due to the higher density and interesting energy sources. For example, molecules like acetone, methanol, even ethyl formate, a molecule that smells like rum, interestingly, have been found in Sagittarius B2, a giant molecular cloud near the center. It's a chemist's treasure trove. It's fascinating to think that while we orbit calmly far away, the center is such a frenetic place, but its influence reaches us. The mass of the central black hole is negligible for the galaxy's overall gravity. The dark matter and stars dominate on large scales. But in aggregate, the central mass concentration anchors the rotation and influences the bar structure that extends across the inner galaxy, which in turn helps shape the spiral arms. It's all connected. At times, I picture the Milky Way's center as a kind of cosmic hearth, a fireplace at the center of a great hall. It may burn low or fiercely, but it's the focus around which the structure of the house is arranged. Right now, our hearth is glowing quietly, but who knows in a few million years or in the past? It might have flared, sending sparks, radiation, winds across the galaxy's inner regions. So as we think of the galactic center, we think of paradox. It is both the brightest concentration of stars and home to the darkest of objects. It's a place where time and space are warped by extreme gravity, yet from which our galaxy's spiral structure gracefully unfolds outward. It is central and crucial, yet largely hidden from our direct view. To feel it, we must rely on instruments and imagination. Let's pause a moment and imagine ourselves floating a few light years from Sagittarius A, shielded safely, looking outward. The sky is ablaze with the glow of 10 million stars. Perhaps we see the spiral arms from the inside, radiant streams extending outward. Above and below, beyond the disk, faint glows hint at the Fermi bubbles. The black hole behind us is invisible, save for the swirl of hot gas around it, making a sort of dim halo. We feel the space-time vibrating with activity. Stars slingshotting by, X-ray flashes from small matter falling in, the hum of dense star clusters. It's both serene in its grandeur and terrifying in its intensity. In the silence of space, this chaos is oddly mute, but one can sense the energies at play. Having dared to visit the heart of the Milky Way, let us journey back outward a bit to consider something the galactic center helped reveal: the rotation curve of our galaxy and what that means, bridging back to our earlier thoughts on the invisible architecture. The rotation curve. One of the most illuminating ways to understand a galaxy is to study how it rotates. Imagine watching the Milky Way spin over time, sped up enormously, of course. How do the stars and gas move as a function of distance from the center? The graph of orbital speed versus radius is called the rotation curve. For the Milky Way, as with many other galaxies, the rotation curve holds a surprising story that forever changed our understanding of the cosmos. In a simple world, you might expect the inner parts of the galaxy to rotate fast and the outer parts to rotate slower, much like planets in the solar system, where Mercury zips around fast and distant Neptune moves more slowly. If most of the mass were concentrated in the center, like the Sun in our solar system, that's exactly what you'd see. Speeds would drop off with distance. However, when astronomers measured the motion of gas and stars at various radii in the Milky Way, they found something astonishing. Beyond a certain point, the rotation speeds did not drop off. They stayed roughly constant or flat, and even out to large radii remained high. In the inner region, inside roughly a few thousand light years, speeds increase with radius as one moves out from the central bulge. This is normal because initially you're still adding more enclosed mass as you go outward, so gravity grows. But beyond the inner bulge disk, instead of peaking and then declining, the curve plateaued. Stars and gas far from the core, tens of thousands of light years out, were orbiting at roughly 200 to 240 kilometers, nearly as fast as those much closer in. This flat rotation curve was one of the key pieces of evidence that led to the concept of dark matter, which we discussed in the invisible architecture. It told us that the mass of the Milky Way keeps increasing with distance far beyond the visible disk. There must be a lot of unseen mass out there providing the gravitational pull to keep those outer stars moving fast without flying away. Without that extra gravity, the outer stars and gas clouds, moving as fast as they do, would escape the galaxy's grip. The rotation curve basically mapped out the presence of the dark matter halo. As you go out, you keep encountering more mass that's not shining. However, even with this general understanding, scientists continue to refine the Milky Way's rotation curve with better data. It's not a perfectly flat line. It has subtle bumps and wiggles. For instance, around the Sun's orbit, 27,000 pounds-li, the speed is around 220 kilometers. Further out, it might gently rise or fall by small amounts. Recent precise measurements from Gaia and other surveys indicated the curve might even decline slightly in the far outer disk, suggesting maybe less dark matter in the outskirts than some models predicted, though the data are tricky. Still, broadly, it remains far higher at large radii than a visible matter-only galaxy would allow. One can think of the rotation curve as a kind of diagnostic of the galaxy's mass distribution. In the Milky Way, it tells us that the luminous parts, stars, gas, are only the tip of the iceberg of mass. The dark halo's distribution is such that even at distances where the starlight fades, mass is still accumulating. Historically, measuring the Milky Way's rotation curve had challenges because we're inside the disk. Astronomers used a clever method, observing the 21 centimeter radio emissions of hydrogen gas in different directions. In certain directions along the inner galaxy, they could measure Doppler shifts that indicated how fast gas was orbiting. By mapping the velocities as a function of galactic longitude and using geometry, they inferred the rotation speeds at different radii. External galaxies provided additional confidence. Vera Rubin's pioneering work in the 1970s on spiral galaxies showed flat rotation curves were common, not just an oddity of the Milky Way. The rotation curve is often plotted with orbital speed on the vertical axis and distance from center on the horizontal. For the Milky Way, it rises from 0 at the very center, though motions there are more random due to the bulge. Peaks around maybe 200 to 240 kilometers in the inner disk, and then stays around that value out to as far as we can measure, maybe 60,000 light-years or more. If the galaxy's mass ended around the visible edge, half 50,000 pounds-li radius, the curve would start dropping, but it doesn't significantly, indicating the halo extends much further. Think of a carousel again, but imagine invisible weights are hidden under the floor, extending way out beyond the visible platform. The horses near the edge keep going fast because those hidden weights provide the gravitational pull. There's also something poetic here. The stars in the Milky Way are essentially flying in enormous circles, guided by gravity's hand. We don't feel this motion sitting here on Earth, but it's real and enormous in scale. Each star's orbit is a balance. Its motion is trying to fling it away, but gravity pulls it in. At the radius of the Sun, that balance has us moving at roughly 500,000 miles per hour around the center. At the edge of the disk, a star might still be moving at 400,000 km/s. The galaxy's rotation is the reason the Milky Way has maintained a disk shape. If it rotated much slower, gravity would collapse more material inward. If it were faster, perhaps the outer parts would break away. Rotation also ties intimately with the spiral structure. The arms are not material arms that rotate like a solid object. They are patterns through which stars and gas move. The differential rotation, inner parts rotating faster in terms of orbital period than outer parts, means any material arm would wind up tighter and tighter. So the prevailing idea is that spiral arms are a kind of density wave that rotates at its own pattern speed, and stars enter and leave it, like cars moving through a traffic jam region. The rotation curve plays a role in where these pattern resonances occur. It's amazing that from the simple question, how do stars move in the galaxy, we unveiled something as profound as dark matter. The rotation curve is like the galaxy's heartbeat chart. For humans, a heart ECG can indicate health or problems. For the galaxy, the rotation curve indicates a hidden vital component. Let's reflect a moment on what it would feel like if we could sense this rotation personally. Right now, sitting or standing, you might feel at rest, yet you are on a planet spinning on its axis, orbiting the Sun, and also careening around the galactic center. The motion around the galaxy is by far the fastest of these at any given moment, since 220 km dwarfs Earth's orbital, 30 km or rotation, still 0.5 km at equator. So we are all passengers on a starship called the Solar System, cruising through the Milky Way at tremendous speed. The stars we see near us share roughly the same orbital motion. They're our fellow travelers. More distant stars, if you track them long enough, show up with different velocities due to perspective and their position. Gaia's measurements of star motions let us see the kinematics in exquisite detail. How some stars stream together in groups, perhaps remnants of disrupted clusters or past mergers. How the disk might have subtle waves or corrugations, possibly from the influence of satellite galaxies, like the Sagittarius Dwarf or LMC. The rotation curve, being flat, implies the presence of that dark halo we spoke of, which itself is a major character in our story. Without dark matter's gravitational support, the Milky Way might not have formed as it did, and the rotation would be quite different. Some alternate theories have been proposed, like modified gravity theories, to explain flat rotation without dark matter, but none have matched all evidence as well as the dark matter halo model for our galaxy and others. From a narrative perspective, the rotation curve is like reading the galaxy's diary in a language of motion. It told us that the Milky Way has more to it than meets the eye, an insight somewhat akin to reading someone's calm outward expression, but sensing an underlying strong heartbeat. It's the clue that led us down the path of acknowledging the invisible architecture in quantitative detail. As we continue outward or onward in our journey, the rotation curve concept will segue nicely into discussing the dark matter halo specifically, since it's responsible for that shape of the curve. We have essentially set the stage. The galaxy rotates in such a way that reveals the dark matter. Now we'll explore that halo in more depth, albeit in a poetic tone, since dark matter is inherently mysterious. So, with stars swirling around us in a gravitational dance and speeds that defy the luminous mass, we prepare to meet the dark halo face to face, or rather, face to something we cannot see, but know is there by its embrace. Dark matter halo. Enveloping the Milky Way like a cocoon is the dark matter halo, a vast and enigmatic component that extends well beyond the visible galaxy. We've already felt its gravitational influence in the flat rotation curve and the invisible architecture. Now let's visualize this halo and contemplate its nature and significance, as if meeting the ghost in our galactic home. Imagine a sphere centered on the Milky Way, perhaps as large as 1,000,000 light-years across, nearly half the distance to the Andromeda galaxy. Within this sphere, sprinkled very lightly, are particles of dark matter, something we do not yet understand fully, be it an exotic particle or something stranger, but which has mass and thus gravity. These dark matter particles neither emit nor absorb light. They pass through ordinary matter, almost as if it wasn't there, interacting mainly via gravity. They are elusive. Billions might be passing through you right now without a trace. Yet, their cumulative effect around the galaxy is immense. They account for about 90% of the Milky Way's total mass. The dark matter halo likely formed early, before the galaxy's stars were born. In the young universe, slight density variations caused some regions to collapse into clumps dominated by dark matter. These were the seeds of galaxies. One of those seeds became the halo of the Milky Way, pulling in gas which then formed stars and the disk within. Over time, smaller halos merged, assembling into the larger halo we have now, dragging their luminous contents, stars, gas, with them. Even today, the halo might have substructure, clumps or subhalos of dark matter, perhaps hosting small satellite galaxies or just invisible on their own. What is the shape of our dark halo? We often imagine it spherical, but it could be a slightly squashed sphere, triaxial, or oblate. Studies of stellar streams, remnants of torn-apart dwarf galaxies, serve as tracers, like throwing paint on an invisible object to see its outline. These studies suggest the halo might be a bit elongated or lopsided, especially given a big lump like the Large Magellanic Cloud may even distort it a bit. But roughly, it's a huge, roundish cloud of mass around the Milky Way. In that halo, aside from dark matter, there's a tiny population of visible things, the halo stars and globular clusters we discussed, and the satellite galaxies orbiting within it. They are like fireflies around an elephant, bright but insignificant in mass compared to the dark matter bulk. If you could view the Milky Way from afar in the dark matter spectrum, whatever that might be, you'd probably see a smooth glow, if dark matter glowed, about 10 times the diameter of the visible spiral, maybe tapering off gradually at the edges, with slight ripples where subhalos might reside. The visible galaxy would lie at the center as a bright jewel in a glass paperweight. This halo is the gravitational cradle of our galaxy. It keeps everything bound together. When our galaxy engages in cosmic interactions, it is the dark matter halo that largely dictates the outcome because it's the dominant mass. For instance, if the Milky Way passes near another galaxy, it's the halos that feel each other first, tugging gravitationally like invisible giants meeting before the visible galaxies ever touch. Dark matter's presence also shields and shepherds the galaxy's content. It provides an additional gravitational well, such that even as the galaxy rotates rapidly, the stars remain secure in orbit. Without the halo, a fast-rotating disk might fly apart. The halo's gravity holds the disk intact, much like an egg's invisible gravitational field might hold a spinning yolk in place, if one can imagine such a thing. What is especially intriguing is that we know dark matter exists through effects like these, but we don't know what it is. It's one of the greatest scientific mysteries of our time. It could be a type of particle left over from the Big Bang that interacts only via gravity and perhaps the weak nuclear force. Many experiments on Earth are trying to directly detect a dark matter particle in underground detectors, so far without confirmed success. It could even be something more exotic, primordial black holes, or something not predicted yet. But in the grand narrative, in the Milky Way's tale, dark matter is a silent character who never speaks, never reveals its face, yet whose actions shape everything. the halo does interact gravitationally with visible matter in ways beyond just holding it. It likely plays a role in how material flows into the galaxy. For instance, fresh gas from intergalactic space might be attracted by the halo's gravity, then slowed or shock heated upon entry. It may accumulate in the halo as hot gas. Some theories say there's a hot circumgalactic medium, a very low density, million-degree gas pervading the halo, detected via X-ray and UV absorption lines. That gas can slowly cool and rain onto the disk, fueling new star formation. So the halo could be seen as the galaxy's reservoir, catching incoming material in a gravitational net. The halo also can capture or destroy other small halos. When a dwarf galaxy ventures close, if the tidal forces from the Milky Way's halo exceed the dwarf's self-gravity, the dwarf gets torn apart. Its stars become streams. Its dark matter likely just assimilates into the Milky Way's halo. Over cosmic time, the halo has probably grown by eating many smaller ones, an unseen feast leaving behind star stream crumbs as the only visible evidence. It's mind-bending to consider that most of the Milky Way's mass lies in this unseen halo. To draw a metaphor, imagine meeting a person and discovering that 9/10 of their body is invisible, and you only see an arm, part of a face, and a foot perhaps. You'd realize you really don't know the full person at all. That's our situation with the galaxy. We see its stars and nebulae, the parts sticking out, but the bulk is hidden. And that is true for all galaxies, not just ours, hinting at something fundamental about the cosmos. For our narration, let's personalize the halo a bit. Think of it as a gentle giant surrounding the bright hubbub of stars. It's mostly quiet, interacting by gravity's pull. It doesn't shimmer or shine, but it has enormous influence. If the disk of the Milky Way is like the visible dance of a music box ballerina, the halo is the unseen mechanism that provides the structure and momentum for the dance. There's also a sense of melancholy with dark matter. It's so important, yet it doesn't partake in the flashy parts of cosmic evolution. No light, no chemistry, no forming of planets. As far as we know, dark matter cannot clump to small scales because it doesn't radiate energy, so it can't cool and collapse to form things like stars or planets. It stays in a large, diffuse halo. It's like a scaffold that builds a cathedral, but once the cathedral, stars, planets, is built, you take away the scaffold's visible role. Yet the scaffold was necessary. We might wonder, do dark matter particles pass through us? Yes, if they exist as particles. Earth is moving through the galaxy's halo, so presumably a wind of dark matter flows through at hundreds of km/s. They rarely, if ever, hit our atoms in a noticeable way, but experiments are trying to see a faint tap of a dark matter particle hitting a detector nucleus. From a philosophical standpoint, the dark matter halo reminds us that much of reality might be hidden from direct view. In the Milky Way, what you see is not all there is. One must infer, deduce, and feel the effects of the unseen. In life, too, sometimes what's important is not immediately visible. It's a nice parallel. Now, another feature of having a dark matter halo is that it extends the influence of the Milky Way far out. There's no clear edge to the galaxy because of the halo. It gradually peters out. This makes the concept of where the Milky Way ends fuzzy. Some define the edge where the escape velocity equals the rotational velocity, etc. But thanks to the halo, one could say our Milky Way has a radius on the order of 300,000 light-years or more, where the density of dark matter merges into the general background of space. The nearest big galaxy, Andromeda, has its own halo, and interestingly, these halos might already be touching or overlapping in the space between Milky Way and Andromeda, like two giant soap bubbles gently contacting. If so, then in some sense our local group, the group of galaxies including Milky Way, Andromeda, and some dwarfs, is one connected structure through the dark matter distribution. It's a lovely concept that even before the galaxies themselves collide, which they will in billions of years, their dark halos have met. In closing our consideration of the dark halo, let's envision drifting outwards from the bright disk into the realm of darkness. As the starlight fades behind us, we plunge into an almost empty vastness. But we're not alone. The gravitational pull is still with us, indicating mass all around like a subtle tension in space. Occasionally we might pass a lone globular cluster or a small satellite galaxy, little islands of light in the dark sea. But mostly, it's quiet and dark. If we could see the dark matter, maybe it would look like a faint mist or swirl around us. Perhaps it's clumpy. Maybe we pass through an invisible cloud that is a subhalo. We wouldn't know, except perhaps by a slight tug. The main Milky Way disk now is a small shining disk far behind, like a distant lighthouse. Yet the domain of our galaxy extends much farther, here in this dark realm. We realize that as we leave the visible behind, the Milky Way's influence has not ended. It extends its gravity out here in the silence. And interestingly, out here, we might find things like star streams and signs of galactic cannibalism, evidence of how the Milky Way grew. So now, let's follow one of those streams of stars, a tenuous bridge of lights crossing the dark halo, which tells the tale of galactic cannibalism, the ongoing process by which our galaxy has consumed others. Star streams and galactic cannibalism. In the Milky Way's halo, if you look closely, with the powerful eyes of missions like Gaia, you'll find stars arranged in long, arcing filaments, as if drawn out into lines by a cosmic comb. These are stellar streams, the remnants of small galaxies or star clusters that ventured too close to the Milky Way and were torn apart. They are the ghostly footprints of past galactic meals, evidence of what we call galactic cannibalism, the process by which our large galaxy grows by devouring smaller ones. Picture a smaller dwarf galaxy, perhaps millions or a billion stars, bound loosely together, orbiting the Milky Way. Over time, gravitational tidal forces stretch it. Stars from the dwarf begin to drift out, forming a stream, trailing and sometimes leading the core of the dwarf, like taffy being pulled apart. Eventually, the dwarf structure dissolves, leaving behind a stream of stars orbiting the Milky Way along what used to be the dwarf's path. These streams can wrap around the galaxy in huge loops. They're faint, but with precise measurements of star positions and motions, we can detect them as overdensities of similarly moving stars. One famous example, the Sagittarius stream, from the Sagittarius dwarf spheroidal galaxy, which has been in the process of merging with the Milky Way for billions of years. The core of this dwarf is still present, a dim, fuzzy galaxy on the opposite side of the galaxy from us, toward the constellation Sagittarius, hence the name. But it's being dismantled. Wraps of its stars have spread in a polar orbit around us. Indeed, part of that stream passes relatively near the Sun's position, though still tens of thousands of light years away. It forms a huge structure encircling the galactic halo. Imagine a gossamer ribbon of stars, too faint to see without telescopes, looping over the top of the Milky Way and around beneath. That's the Sagittarius stream. Another, the GD1 stream, thought to be from a globular cluster that was torn apart. Or the Palomar 5 stream, another shredded cluster leaving a thin stream behind. There are others like Orphan Chenab stream, poetically named because the progenitor is gone, an orphan, and the Helmi streams, discovered by an astronomer, Amina Helmi, which are remnants of a dwarf galaxy that merged early on. And then, one of the most significant events in the Milky Way's history has been deduced by studying the halo star's motions and chemistry, a collision about 8 to 11 billion years ago with a dwarf galaxy often called Gaia Enceladus, or the Gaia sausage. This oddly nicknamed object was a fairly large dwarf galaxy that smashed into the early Milky Way. Many of the halo stars and the halo's inner portions have orbits and compositions indicating they came from this event. The name sausage comes from a pattern in velocity space that looks like a sausage shape when plotted, identified in Gaia data. This merger is believed to have puffed up the Milky Way's thick disk and given it a lot of its halo. In a sense, we are partly a chimera. Our galaxy is partly built from the remains of that galaxy. After the collision, the stars of Gaia Enceladus were strewn into radial orbits, going out and back in, which is why in velocity space they have high radial motions but not much rotation, giving that sausage signature. That event likely also caused a burst of star formation and altered the structure of our young Milky Way. Galactic cannibalism may sound violent, and indeed on a cosmic scale, it is a sort of violence. But remember, stars are so far apart that when two galaxies merge, individual stars almost never collide. Rather, the system's gravitational fields merge. The smaller galaxies' stars simply find themselves gradually reassigned to orbit in the gravitational potential of the bigger galaxy, rather than their original small one. The violence is in the gravitational forces that rip the structure apart, and any gas in those galaxies can get compressed and create flashes of new stars, starbursts, or feed the central black hole, etc. Over time, the smaller galaxy is fully digested, its stars now just part of the halo or disk of the Milky Way, its distinct identity gone. Our Milky Way has probably consumed dozens of smaller galaxies over its lifetime. Some were long ago. Their stars are thoroughly mixed, and we only find hints by finding stars with unusual chemistry or orbits. Others are ongoing, Sagittarius, or recent, like Gaia Enceladus. 10 billion years is recent in a 13 billion year life. This process is common in the universe. Big galaxies like ours grew by hierarchical merging, assembling from smaller pieces. Even the Large Magellanic Cloud, LMC, that orbits us now is destined for this fate. The LMC and its smaller companion, the SMC, Small Magellanic Cloud, are falling toward the Milky Way. Within a few billion years, they might merge into us. Some models say the LMC will fall in sooner than Andromeda's arrival. When that happens, it will induce new star formation, perhaps create new streams, and add its stars, and even its own central black hole. The LMC likely has an intermediate mass black hole, which may merge with our central black hole eventually. This cannibalistic side of the Milky Way is a reminder that galaxies are not static islands. They are dynamic and continually evolving. For smaller galaxies in our vicinity, the Milky Way's gravity is a force of destiny. Over time, the Milky Way will incorporate many of them. It's almost like the mythology of Cronus devouring his children, except the Milky Way devours smaller siblings. But it's not malicious, it's just gravity doing its inexorable work. The stellar streams left behind have a serene beauty to them. I like to think of them as cosmic rivers in the galactic halo, or perhaps the fossil rivers of what once were independent galaxies. They also serve as signposts. For instance, the way a stream's path bends can tell us about the shape of the dark matter halo. The stream is essentially a test particle feeling the gravitational field. One day, maybe we'll map dozens of streams and thereby map the dark matter distribution precisely. Also, some globular clusters might be immigrants from swallowed galaxies. Some clusters have different properties that suggest they originally lived in a dwarf galaxy that got merged, and the cluster got adopted by the Milky Way. From our vantage in the solar system, these events are subtle. The night sky doesn't obviously show a stellar stream to our naked eyes, except maybe one can argue that the Milky Way's own band had to be recognized as our galaxy, not a stream through it. That was another story from Shapley versus Curtis. But through telescopes, we can detect certain patterns. For example, the Sagittarius dwarf galaxy can actually be imaged as a faint concentration of stars, only discernible with telescopic surveys. And if you plot the positions of certain types of stars, like RR Lyrae variables or blue horizontal branch stars, which often reside in old populations, at large distances, you can see overdense bands corresponding to known streams. Galactic cannibalism will continue into the future. Eventually, the Milky Way itself will be devoured, or rather, merged, when we collide with Andromeda. But by then, in that merged entity, all the smaller galaxies we had left, maybe the Triangulum galaxy, M33 possibly, plus any dwarfs, will fall in as well to form one big elliptical or diffuse galaxy. Our local group will become one large Milky Andromeda hybrid, sometimes playfully called Milkomeda. The notion of cannibalism is stark, but there's a constructive side. Each merger brings new material. The mixture of gas can spur star formation. New stars, clusters, maybe even new nebulae and structures are born from the union. It is a mode of cosmic renewal. The halo's very existence as a blended repository of many origins gives the Milky Way a kind of genealogical richness. If you take one halo star, measure its chemistry, you might find, oh, it has very low magnesium relative to iron that matches stars from this specific dwarf galaxy's pattern. That star might truly be from a galaxy consumed 10 billion years ago. It's like an immigrant star now living in the Milky Way, but carrying the accent of its birthplace in its elemental makeup. In that sense, the Milky Way is a melting pot of stars from different lineages. Much like modern cities contain people from diverse origins, the Milky Way's halo contains stars from a variety of prior smaller galaxies. We can stand under the night and not know that a star twinkling above might have originated outside our galaxy entirely. But the science tells us that's likely the case for many halo stars. Let us imagine following a stream. We drift along a line of stars in the halo. They stretch before us, hundreds of light years wide, but tens of thousands of light years long, gently curved around the galaxy. They are relatively sparse compared to the disk. If you were in the middle of a stream, you might still have to travel many light years to go from one star to the next. But relative to the emptiness around, it's a marked overdensity, like a barely visible road in a desert. We follow it inward. It leads us to a dwindling remnant of a once proud dwarf galaxy, perhaps a tightly bound cluster of stars that was its core. We follow it outward. It fades into the background of the halo. Over time, even the stream will diffuse further, as stars in it gradually spread out due to slight differences in their orbits. Streams are transient over billions of years, eventually becoming part of the general smooth halo background. The concept of galactic cannibalism invites philosophical reflection. Nature seems harsh on these scales. Big galaxies eat little ones. But it's also just the flow of gravity, not driven by intention. And from the ashes of that process arises something new. A larger galaxy, possibly capable of forming new stars and even new planetary systems that would not have existed otherwise. So there's destruction, but also creation in a new form. Now, beyond streams, we should note that not all satellites are completely destroyed yet. Some still exist around us. The satellites are basically meal preparation in a sense. We've touched on that, but it's worth giving them their spotlight next, before they too eventually face either merging or just orbiting ad infinitum. So let's now visit those satellite galaxies. The companions currently in the Milky Way's retinue, orbiting like the moons of a planet, though on a much bigger scale, some destined to become the next star streams in the far future. Satellite galaxies. The Milky Way is not alone in the cosmic ocean. It is accompanied by a swarm of smaller satellite galaxies bound in its gravitational embrace. These satellites are galaxies in their own right, but much smaller and fainter than the Milky Way, and they orbit around our galaxy like tiny fish around a great whale. They provide a sense of context. Our Milky Way, large as it is part of a local community of galaxies. The two most famous satellites are visible to the naked eye from the southern hemisphere: the Large Magellanic Cloud, LMC, and the Small Magellanic Cloud, SMC. These appear as hazy, cloud-like patches in the deep southern sky, so much so that early explorers thought them to be clouds, hence the name. In reality, they are dwarf galaxies. The LMC is a barred spiral or irregular galaxy about 163,000 light-years away, roughly 1/10 the mass of the Milky Way, containing on the order of 30 billion stars. The SMC is about 200,000 light-years distant, with perhaps a few billion stars. These two are likely a bound pair and have been orbiting the Milky Way together. They have had a huge impact on our galaxy. Their gravity may be tugging on our disk, possibly causing asymmetries and warps, and gas outflows from them, the Magellanic Stream we mentioned, are feeding our halo with fresh material. The Magellanic Clouds are rich in gas and still forming stars. They have vibrant nebulae like the Tarantula Nebula in the LMC, which is one of the most active star-forming regions in the local group, a cauldron of massive stars and supernova remnants. If we look at them with telescopes, we see a flurry of star clusters and nebulae. They are like miniature versions of galaxies that remind us of how the Milky Way might have looked when it was smaller, or how galaxies across the cosmos often appear. Beyond the clouds, the Milky Way has dozens of dwarf spheroidal galaxies as satellites. These are faint, fuzzy objects scattered around the halo, many discovered only in recent decades with deep imaging surveys. They have poetic names often after the constellations they're found in: Draco, Ursa Minor, Sculptor, Fornax, Carina, Sextans, Sagittarius, which we already discussed being cannibalized, and many ultra-faint dwarfs like Willman 1, Segway 1, Bootes 1, etc. These dwarfs typically have only a few million to a few tens of millions of stars. Some of the ultrafaints just thousands of stars. They are heavily dominated by dark matter, interestingly, meaning the visible stars are just a tiny fraction of their mass. They're like little dark matter mini halos with a sprinkle of stars. Because of this, they are dynamically very stable, lots of dark matter to hold them. They have very old stellar populations, indicating they stopped forming stars long ago. Perhaps their gas was stripped early by the Milky Way, or they used it up quickly. They appear as little smudges in telescopes, often requiring long exposures to discern from foreground stars. One might ask, how many satellites does the Milky Way have? The number keeps growing as we find fainter ones. Currently, known ones are on the order of 50 to 60. The bright ones can be counted on fingers: Magellanic Clouds, Sagittarius, and maybe a dozen classic dwarfs discovered mid-20th century. But newer digital sky surveys are revealing extremely faint ones that push the limits of detection. We suspect there might be even more, lurking in parts of the sky not fully surveyed or hidden by the Milky Way's disk, or simply too faint to pick out easily. These satellites orbit at various distances. Some, like the Magellanic Clouds, are relatively close, under 200 kli. Others, like Leo 1, are quite far, over 800 kli. They orbit in what seems like somewhat random orientations, though there's some research suggesting maybe some align in a kind of plane, or come in groups possibly associated with cosmic filament structures. It's still debated if there's a satellite plane, or if that's a chance arrangement. The gravitational dance between the Milky Way and its satellites can have effects. The LMC, being the largest, is thought to be on its first approach possibly. Some studies propose the LMC might have only recently been captured. If so, the halo of the Milky Way might be moving a bit in response. The center of mass of the Milky Way LMC system might shift, causing our galaxy to slightly wobble. Some recent papers discuss the idea that ignoring the LMC's influence could bias measurements of the Milky Way's mass. Each satellite galaxy is like a chapter in the Milky Way's story. Some might be future meals. Some might just remain satellites indefinitely. For example, ultra-faint dwarfs might not easily merge because they're so small and diffuse. They might just get gradually stripped away over time. Others, like Sagittarius, are clearly on the menu. The Magellanic Clouds might merge soon, in cosmic terms, say within 2 billion years possibly for LMC. Satellites are also interesting as laboratories. Being simpler and smaller, they help us test models of dark matter on small scales and star formation in tiny potentials. They show that not all galaxies look like grand spirals. The majority in the universe are actually these small dwarfs. Poetically, I think of the satellites as a retinue of companions or children of the Milky Way. If the Milky Way is a great tree, these are the saplings around its base, some of which will eventually be reabsorbed into the soil to feed the great tree. Others may be transplanted by cosmic currents. They remind us of scale. What's small and faint compared to the Milky Way might itself hold thousands or millions of stars, and likely countless planets. Yes, consider that too. Each dwarf galaxy, even if it has 1,000,000 stars, likely has planets. Could there be life in a satellite galaxy, gazing at the Milky Way as a giant spiral in their sky? Perhaps a planet in the LMC has a view of our galaxy somewhat like we see Andromeda, a big object in their night sky. Quite a perspective. Culturally, the Magellanic Clouds were known to peoples of the southern hemisphere for millennia. European explorers in the Age of Sail took note of them during voyages, hence named after Magellan by Pigafetta, though many indigenous cultures had their own names. They have always been a curiosity. What are these patches? Only in the 20th century did we measure their distance. Harlow Shapley did important early work on the SMC's distance using variable stars, and realized they are separate galaxies outside our own. The awareness that the Milky Way had companions was part of the bigger picture. Not only is the Milky Way not the whole universe, as the great debate settled by recognizing other galaxies, but even our galaxy itself has a system of smaller galaxies around it, a sort of microcosm of the macrocosm. We have our own mini-local group around just us. One of the nearest dwarf satellites is the Canis Major overdensity, discovered around 2003, which might be the core of a dwarf galaxy in process of merging, only 25,000 Poundsley from the center, which is inside the disk's radius. It's controversial, but there is evidence of a cluster of stars near Canis Major direction that could be a merging dwarf. If true, it's basically getting eaten now, and might be responsible for some rings of stars in the disk, like the Monoceros ring. This shows how the line between satellite galaxy and galactic structure blurs when cannibalism is happening. In the cosmic future, after Andromeda merges and everything settles, likely many of these current satellites will either be part of the big elliptical or flung out. Right now, they are like little birds around a big one, but when big birds come together, Milky Way plus Andromeda, the flock gets reconfigured. To visualize satellites, think of a three-dimensional model. At the center, the Milky Way disk. Dotted around at various distances, small fuzzy blobs. Some closer in, Sagittarius trailing streamers. Some mid-range, LMC, SMC, Fornax, etc. Some far out on the fringe, Leo Were, near edge of our halo. They each orbit at tens to a couple hundred kilometers speeds in some orbit. Over billions of years, we'd see them swarming, occasionally spiraling in. Interestingly, satellites can also survive if in stable orbits, especially if they're in a distant orbit and not a lot of dynamical friction, which slows down orbits of big objects moving through halos. Ultrafaints might hang around indefinitely if not disturbed. The LMC, being relatively massive, will probably spiral in faster due to dynamical friction. It's like how in a fluid, a big object slows quicker than a small one due to drag. We should also mention satellites like Ursa Minor Dwarf, Draco Dwarf, faint but historically known, discovered in 1950s from photographic plates. And Fornax Dwarf has some globular clusters of its own, a dwarf galaxy that has its own satellites, mini globular clusters, adding layers. So, the Milky Way is a system with subsystems. It's hierarchical. As part of our journey, perhaps now we stand metaphorically at the edge of the Milky Way's domain, looking at a sky not dominated by a single galaxy, but by many small companions scattered around. Perhaps from a vantage point in the halo, we could see the Magellanic Clouds off to one side, maybe glimpses of other dwarfs as faint smudges if our eyes could integrate light long enough. It would emphasize that the Milky Way is the central hub of a small cluster of galaxies. With satellites in mind, one naturally wonders, at the core of each satellite, is there something like a black hole or remnant? Possibly, the LMC likely has one, others might not. Dwarfs might have only intermediate mass or none. But we know the Milky Way has one for sure at the center. And not just the central black hole. There are stellar mass black holes and other remnants peppered throughout. Let's now contemplate those black holes and remnants that permeate the galaxy after millions of star lives. The skeletons in the galactic closet, so to speak. Black holes and remnants. Throughout the Milky Way, hidden in the darkness, lie the corpses of stars, white dwarfs, neutron stars, and black holes, the remnants left when stars die. These objects are the end states of stellar evolution, and they are as much a part of the galaxy as the shining stars, though they emit little or no light of their own, apart from some exotic behaviors. In a sense, they are the galactic ancestors, the silent remnants of previous generations of stars that have completed their life cycle. Start with white dwarfs. These are the exposed cores of low to medium mass stars, like the Sun, after they shed their outer layers as planetary nebulae. A white dwarf is about the size of Earth, but with mass around that of the Sun, incredibly dense. Our galaxy is teeming with them. Every star less than about 8 times the mass of the Sun will end as a white dwarf. Given the Milky Way's age, billions of such stars have already gone through that process. It's estimated there are many billions of white dwarfs in the Milky Way. They quietly cool and fade over time, a process that takes longer than the current age of the universe to go completely dark. So even the oldest white dwarfs, perhaps 12 billion years old, still glow faintly red or infrared. In the thick disk and halo, one can find very old, cool white dwarfs that are barely luminous. These are sometimes called black dwarfs in the making, though not fully black yet. The Hubble Space Telescope has observed some of these ancient white dwarfs in globular clusters, giving us clues to ages. They're neutron stars. These are the collapsed cores of massive stars, 8 to 20 solar masses originally, that went supernova. They cram more mass than the Sun into a sphere only about 20 kilometers across. A neutron star is so dense that a teaspoon of its material would weigh billions of tons. There are likely hundreds of millions of neutron stars in the galaxy, though we only detect those that reveal themselves via radio pulses or X-ray emission, etc., a small fraction. Many neutron stars are observed as pulsars, lighthouses of radio or even optical X-ray beams sweeping the sky. The Milky Way pulses with thousands of known pulsars, each a neutron star spinning rapidly. Some spin hundreds of times per second, millisecond pulsars, often found in globular clusters or as remnants of certain binary evolution channels. These are like cosmic clocks, and they even help us detect gravitational waves background or probe the interstellar medium via dispersion of their signals. Neutron stars also can be in binary systems. Sometimes 2 neutron stars orbit each other. We've detected those by their gravitational wave in spiral, like the famous one that produced both gravitational waves and a gamma-ray burst observed in 2017. Some neutron stars pull gas from a companion, flaring as X-ray binaries or even undergoing occasional outbursts when that gas triggers nuclear fusion on the neutron star's surface. These are X-ray bursters. And then, black holes. Aside from the supermassive one at the center, the Milky Way is littered with stellar mass black holes, formed by the collapse of stars above roughly 20 solar masses, or from mergers of neutron stars, etc. How many black holes? Possibly tens of millions. Each typically 5 to 15 times the Sun's mass, some more if formed by mergers. They are invisible unless actively accreting, pulling in gas, which then emits X-rays. Many have been found as X-ray binaries, where a black hole orbits a normal star and strips gas from it, forming a hot accretion disk that emits X-rays. Famous examples: Cygnus X1, the first strong black hole candidate, which is a stellar black hole consuming mass from a blue supergiant, or V404 Cygni, another volatile black hole binary that has dramatic outbursts. Most stellar black holes, however, might just roam quietly. One was recently found via gravitational microlensing. It passed in front of a background star, and the star's light brightened as the black hole's gravity bent it. That was our sign of an isolated black hole. The detection suggested a 7 solar mass black hole about 5,000 light away, dark and solitary. These remnants, white dwarfs, neutron stars, black holes, essentially form a kind of invisible substructure in the Milky Way. If you could see them all with some special glasses, the galaxy would have a faint glow or speckles from myriad white dwarfs in the disk and bulge, little spark-like pulsar beacons, point-like masses warping light, black holes. There's even speculation about intermediate mass black holes, hundreds to thousands of solar masses, possibly lurking in the centers of some globular clusters or dwarf satellite cores. We should also consider black hole binaries merging. LIGO detects such events likely from distant galaxies, but they could happen in our galaxy too, though none detected from within our galaxy yet, because they are rare per galaxy. If two black holes merge in Milky Way, it would release a burst of gravitational waves that we could detect. And neutron star mergers, aside from gravitational waves, they can eject heavy elements. So some of the gold or platinum on Earth might owe to a neutron star collision in the Milky Way's past that seeded heavy elements into a gas cloud that formed our solar system. The presence of remnants also provides continuity. A star dies, but part of it lives on as a remnant. For example, when the star that went supernova to create the Crab Nebula did so in 1054 AD, seen by Chinese astronomers as a guest star, it left behind the Crab pulsar, which still spins and powers the nebula's glow. The Milky Way likely experiences a supernova roughly once every century or so, though it's been a while since one seen by the naked eye, possibly because dust obscured a few. Each supernova adds a neutron star or black hole to the population. Also consider planetary nebulae, the colorful shells of gas from red giants casting off their layers. At the center of each is a new white dwarf. The galaxy has thousands of planetary nebulae visible, each an announcement: a white dwarf is born here. They are ephemeral. The nebula fades after 10,000 years, leaving just the white dwarf. The distribution of remnants is interesting. White dwarfs are everywhere: thin disk, thick disk, bulge, reflecting where stars like the Sun and smaller have lived and died. Neutron stars and black holes are mostly from massive stars, which mostly form in the disk, spiral arms. So their remnants should be in the disk, though some get kicked at birth. Pulsars often have high velocities due to supernova kicks, launching them out of the plane. Some even escape the galaxy if the kick is strong. So neutron stars might have a thicker distribution due to kicks. Black holes might get smaller kicks, maybe some kicks if asymmetry in supernova. So there could be black holes sailing in the halo or escaping as well. One evocative element: some remnants become zombie stars. White dwarfs can accrete material from companions, and if they reach 1.4 solar masses, Chandrasekhar limit, they explode as type Ia supernovae, which are important standard candles for cosmology. So even after death as a white dwarf, a star might have a spectacular thermonuclear rebirth explosion. Neutron stars too can have second lives, spinning back up by accreting matter. Millisecond pulsars are old neutron stars sped up by binary accretion, turning them into whirling beacons again. And black holes might occasionally flare if they consume a passing gas cloud, or even tear apart an unlucky star that wanders too close. Though that's more for big BHs like the center BH. Stellar black holes have small reach, but can still disrupt planets or smaller stars maybe. So, the Milky Way is somewhat of a graveyard entwined with a nursery. New stars are born from gas, often enriched by the deaths of old stars. And the dead stars themselves persist as these remnants, continuing to contribute gravitationally and sometimes in energy outbursts. Even smaller remnants, brown dwarfs, failed stars, substellar objects, and black dwarfs, cooled white dwarfs, none yet fully black, could be considered part of the population of faint objects bridging the gap between stars and remnants. Brown dwarfs are like forever fetal stars that never ignited hydrogen. There are likely as many, if not more, brown dwarfs than stars, lurking with low heat and faint infrared glow. They're not remnants, since they never fully were stars, but they add to the inventory of dark objects. The interplay of remnants could also create exotic phenomena. For example, a neutron star and a white dwarf binary, or a black hole swallowing a neutron star, could produce interesting events like gamma-ray bursts, though those typically happen in distant galaxies. Philosophically, the existence of these remnants is a reminder of mortality and memory. The Milky Way carries its dead with it. Unlike living creatures where corpses decay and disappear, in the galaxy the corpses remain for eons, influencing the environment. The remnants contain clues of their progenitors, like pulsars have spin rates and magnetic fields telling of the original star's core. White dwarfs have composition layers that tell of how the star ended nucleosynthesis. One might imagine each remnant as a kind of memory stone. If we could read them perfectly, we'd know about the star that once shone. Some white dwarfs have atmospheres of hydrogen or helium or carbon, telling what outer layer was left. Some neutron stars have extreme magnetic fields, magnetars, hinting at properties of the collapsed core. As we sail around the galaxy, every now and then we might pass invisible mass points, a black hole here, a neutron star there. Only a chance X-ray or radio emission or gravitational lens effect gives them away. Also, not to forget supernova remnants, not the compact object, but the blast wave and expanding cloud of gas like the Veil Nebula or Cassiopeia A's shell. These are ephemeral compared to the remnant core, but they, for a few thousand years, mark the spot of a stellar death like a wreath. The galaxy has many supernova remnants, observable in radio or X-ray, many more unobserved likely. They contribute to heating cosmic rays, etc. Thus, black holes and remnants add a quiet, somber layer to the Milky Way's composition. Unseen but present, silent but significant. They also connect to next topic, the central black hole we covered, and the future collision with Andromeda will eventually see black holes merge too, the central ones. But first, let's focus on that future collision. However, perhaps it's good narrative to mention, as time goes on, these remnants accumulate. Far in the future, after star formation ceases, trillions of years ahead, the galaxy will be mostly remnants. White dwarfs turn to black dwarfs, neutron stars cooled, maybe proton decay gone, black holes slowly evaporating via Hawking radiation over unimaginable times. That's the ultimate fate scenario. So in a way, these remnants are hints of what the galaxy will become in the distant, distant future. A graveyard with no new stars, just ghosts slowly fading. But before that final fade out, a dramatic event awaits. The collision with Andromeda, M31. That's a nearer term, in billions of years, future, that we should explore now. The future collision with Andromeda. In the cosmic dance of galaxies, the Milky Way and the Andromeda galaxy, our nearest large neighbor, are destined to collide. It's a fate set by gravity, a meeting foretold by the motions we observe today. Approximately 4 billion years from now, when our sun will be approaching old age, the serene night sky as we know it will undergo a radical transformation as Andromeda draws near, eventually merging with the Milky Way in a grand embrace. Let's set the scene. Andromeda, also called M31, is currently about 2.5 million light-years away, visible as a faint smudge in the constellation Andromeda. It's a spiral galaxy, somewhat larger than the Milky Way, perhaps containing 1 trillion stars. We are on a slow collision course. Andromeda is moving towards us at about 110 kilometers, as seen by the blue shift of its light. There's also likely some sideways motion, but even with that, simulations suggest a collision is likely given the strong gravitational attraction within our local group. Fast forward a couple billion years. Andromeda looms larger in the sky. To future inhabitants of Earth, if any remain or if Earth is still habitable then, as the sun will be heating up, Andromeda might appear as a giant spiral, filling a good portion of the sky, growing brighter and more detailed each eon. Its spiral arms could become discernible, and its central bulge would shine like a hazy second Milky Way band across the heavens. As the two galaxies near, their gravitational interactions will begin to disrupt both. Long before the cores meet, their halos and outer disks will clash. Gas clouds in the outer regions might slam into each other, triggering bursts of star formation. So we may see bright new star clusters and nebulae igniting in the collisional interface. The sky might become littered with brilliant O-type star clusters as the galaxies disturb each other's gas. Eventually, the galaxies will interpenetrate. Unlike a car crash, stars mostly do not hit stars because of vast distances between them. Instead, the two stellar disks will pass through each other like ghosts, but gravity will yank on each component, distorting shapes. Tidal tails of stars might fling outwards, great arcing streamers thrown into intergalactic space. Perhaps some stars, and potentially their planetary systems, will be tossed into new, wildly different orbits, some even ejected into space. Our solar system might be largely unaffected physically. The chance of direct close encounters with another star is small even in a merger, though not zero. But the night sky would be chaotic, new constellations of unfamiliar stars, as Andromeda's stars mix with ours. The black holes at each galaxy's center, each millions or billions of solar masses, will spiral toward each other over time, eventually coalescing into an even more massive black hole, after performing a sort of gravitational dance that radiates gravitational waves. When those two black holes finally merge, they will send ripples through space-time. Some future gravitational wave observatory might detect the echo of that event if any observers remain. The merged black hole will likely become active, consuming gas shaken into the center, perhaps lighting up as a quasar for a short time, shooting jets of radiation. During the interaction, the structure of both galaxies changes. The orderly spiral patterns will become twisted and then dissolved. Over a few billion years of alternating passes, these collisions often involve the galaxies swinging through each other, then slowing, coming back for another pass, like oscillating before finally coalescing. The stars' orbits will randomize. Eventually, what emerges from the wreckage is not a spiral galaxy at all, but probably a giant elliptical galaxy, a more amorphous, three-dimensional ball of stars with no distinct disk or arms. This new galaxy has been nicknamed Milkomeda by some, a portmanteau of Milky Way and Andromeda. It will contain nearly all the stars of both galaxies, plus any satellites involved, but arranged in a new way, many on long, eccentric orbits forming a huge elliptical distribution. The gas, much of it likely either used up in starbursts or heated and expelled, might not form a disk, so star formation might slow drastically after the merger consumes the easily formed stars. For any beings at that time, the concept of the Milky Way or Andromeda as separate entities will be meaningless. There will be just one great galaxy filling the sky with a golden glow of billions of stars in every direction. This collision is not something to fear on a human timescale. 4 billion years is far beyond human or even Earth's future. The Sun will be in a red giant phase in about 5 billion years, possibly swallowing Earth. But as part of the galactic story, it's a dramatic climax. Our galaxy, which has been relatively isolated aside from munching dwarfs, will meet its equal and merge, fundamentally altering its identity. Interestingly, the merging will likely bring in Andromeda's own retinue of satellites, and our own, mixing them all. Maybe the Triangulum galaxy, M33, another member of the local group, will get involved or orbit the merger. Many of the satellite galaxies might either merge into the big one or remain as orbiting clusters of stars or get flung out. From a vantage point within the merging galaxies, cosmic events like starbursts might be visible. Perhaps multiple supernovae popping off as new massive stars quickly evolve. Globular clusters could be jostled and some might be thrown into intergalactic space or form anew from colliding gas clouds. The night sky during the merger would likely have many more bright stars due to starbursts and diffuse light from the mass of stars. Perhaps the concept of night might get a bit eroded at some phases as more light fills the sky. However, given the scales, even a merger wouldn't make the sky bright like day. It'd just have more interesting features. Galactic collisions also produce rings and shells sometimes in the stellar distribution, visible long after, and trails of stars might form tidal streams connecting outward. Once the dust settles, literally, much dust might be cleared by starbursts and AGN feedback. The new combined galaxy will shine for trillions of years as it slowly uses remaining gas, then coast into a long, dark era. But by then, local group has become one big, gravitationally bound island universe. And due to the accelerating expansion of the universe, distant galaxies would have receded beyond visibility. So in far future, the merged galaxy will be quite alone in terms of observable universe, apart from maybe its local cluster. But focusing back on now, the knowledge of this future event is one of the marvels of modern astronomy. We have essentially predicted a cosmic event far beyond any human timeframe. It gives a sense of inevitability, but also continuity, that the cosmos has its timetable and flows that will go on without us. If we put ourselves poetically into that future scenario, try to imagine Earth's sky, say 3.75 billion years from now. Andromeda's disk spans the sky, maybe tens of degrees across, a glittering spiral visible even in daylight, perhaps as a faint structure. Then, in 500 million more years, the first close pass occurs. The sky might erupt with new stars. Perhaps the Milky Way's band in the sky distorts into weird shapes as Andromeda's stars join it. In 1 billion more years, multiple bands or a chaotic scatter of stars overhead as everything mixes. By 6-7 billion years from now, a smooth, glowing ellipsoidal distribution of light in the sky with no Milky Way band at all, just an all-sky faint glow, maybe thicker toward the center of the new galaxy. All the while, as an observer, you would have had to withstand the sun's red giant expansion, etc. But perhaps humanity's far descendants could watch from some other corner, or through robotic eyes. It's a scene for science fiction, but one grounded in astrophysics. Galactic collisions are common in the universe. Many galaxies we see are in collision or merged. Our own just hasn't had a major collision recently. The last big one might be that Gaia-Enceladus event 10 years ago. So the Milky Way has had time to be a nice spiral. Andromeda too had mergers. It has a big bulge indicating past action. Now these two big ones will make one larger elliptical. Ellipticals typically have older stars and less gas afterwards. One could wonder about life consequences. Any risk to the solar system? Direct collisions of stars are extremely unlikely. However, passing stars could disturb the Oort cloud, comets, and send comets inward, raising the risk of impacts for planets. Also, if the sun's orbit is altered, it could experience changes in environment, maybe moving to a region with more supernovae or radiation. It's possible that life on Earth by then is gone due to sun's evolution, but if not, the merger could bring some gravitational nudges. But Earth's existence is precarious with the sun's changes anyway. Our collision with Andromeda is often portrayed as violent, but in human terms, it's a slow-motion event spanning billions of years. It will not destroy either galaxy entirely, but transform them. It is an act of creation as much as destruction, creating a new galaxy from two. As we consider that future, it's a reminder that change is the constant. Even the majestic spiral of the Milky Way is transient on cosmic time. The cosmos builds and rebuilds structures over time. Nothing stays the same. Galaxies grow, merge, fade. Now, coming back to a present perspective, one might ask, how fast are we moving right now and toward what? Which leads to consider the speed of motion more generally, not just relative to Andromeda, but all the motions we partake in. We have touched on orbital speeds around the galaxy, but perhaps dedicate a section to the myriad motions, the speed of stars, of the sun, of the galaxy moving through the universe, etc., to capture the dynamic nature.